And now she looks close.
See,
that makes such a difference.
Yeah.
It's a little bit about like what Samsung did for his show.
Right.
Yeah,
How are you?
that's nice talking yesterday.
Yeah,
Oh, thank you.
any closure.
Yeah.
Glad that you were listening remotely.
And then of course, the changes in number of levels, you know,
Yeah, I mean,
that's just more subtle.
And this makes more sense as well because
This
you're
weekend
doing,
was pretty
you know, pressure weighted
It sucks to be sick on the weekend. Like,
energy calculation was before as well.
Yeah.
Because
Ideal time to be sick. Yeah.
And of course, the difference between
Is
a
it busy?
100 meter
during
level
work,
versus a
right.
500 meter level.
No, because I feel like
Is
a work
that
is
chicken?
busy, then the fatigue.
It's a subtle business.
Oh, right, yeah.
Really like that.
I feel like you're becoming a bit of a dictator.
He likes it.
I know, it's quite refreshing.
All right, well, welcome to the AMWG only meeting. If you want to hear about chemistry and whole atmosphere, you're in the wrong room. That's taking place over in the Damon room. So this morning, we're going to talk about boundary layers and microphysics. And then after lunch, we're going to go into machine learning and ultra high resolution stuff and die cores. Please eat the cake out there, otherwise it's gonna go away. This is the cake from yesterday, so I think it's the last. So if you have kids or something, just take it as much as you want. With that, I'll let Adam take the microphone here and talk about, I believe it's Club MF. Yeah, once you get used to it, it's nice, but yeah, once you get used to it. And oh, I forgot to mention, we have one cancellation, Justin's ADF talk, he's sick, so I won't stop anybody to, well, I'll let the discussions run as long as you want, since we have extra time. So go ahead.
Good morning, everyone. So we have talked about how there's a Club L's branch, there's a Club Tau's branch. Now I'm going to talk to you about Club MF. So there are three separate things. This is one of the main deliverables of the EMF CPT project.
So sorry to interrupt, it's not showing the correct screen.
Oh, okay.
Sincere apologies.
I heard the chat was live and active. Okay, hopefully everyone can see that online. So this is one of the primary deliverables of the EDMF CPT team. Dragos here is the PI from JPL, who was the NCAR co-PI. The outline for my talk is just going to go over the formulation and some new mods we made to the entrainment rates. I want to go up our new merged up code base, and I'll explain what that means when I get to it. And then we're going to look at deep convection in Club MF versus Camp 7. And lastly, we're going to talk about incorporating cloud aerosol interactions in the Club MF. So this is sort of the boilerplate overview of why we're doing this. So we're taking this eddy diffusivity mass flux approach and applying it to CAM. The eddy diffusivity mass flux approach parameterizes your turbulent fluxes using a downgradient eddy diffusivity mixing, which is typically what PBL schemes use, and they're augmenting them by explicit ensemble of mass flux plumes. And these mass flux plumes are initialized from a PDF of surface flare thermodynamics, and so you can have multiple plumes in a grid cell. And they you can have different types of convection in a grid cell using these multiple plumes. In CAM 6, CAM 7, our PBL scheme is club, and it also is a shell convection. And so We're actually considering that the club is going to be doing the ED part of the EDMF, and we're going to augment club with mass flux plumes. And we send our, and this is a unified convection scheme because we send our mass flux attendees into the club solver. So all convection in the model is in club MF. So it's an explicit ensemble of entraining plumes. It's very important to focus on the entrainment because this isn't a model where we're closing our mass flux spaces on large-scale balances like quasi-convective equilibrium, which is what you would typically use for a deep convection scheme. Instead, we're sort of integrating our plume upwards, computing the buoyancy, the vertical velocity, go to the next level, and when that vertical velocity goes to 0, that's when it terminates. So there's no balance that's determining that vertical velocity, it's just evolving according to the profile, and so that profile is very sensitive to the entrainment rate. And the way that we parameterize entrainment is after a Ramsden-Kwong, and it's effectively we have this entrainment length scale, so the distance a particle can travel before it experiences one entrainment event. And that determines the shape of a Poisson distribution that we will sort of randomly draw from to provide some stochasticity in our entrainment rates. But the most important parameter is the entrainment length scale as it controls the shape of the Poisson distribution. And so the way that I've parameterized the entrainment length scale is a function of two parameters. One, it's the height of the maximum height of the plume ensemble at prior time steps. And so the entrainment rate at the current time would be a function of the height of the plume ensemble averaged over the prior time, or you can even average it over multiple prior time steps. Similarly, we have a cold pool feedback that once we start to form precipitation and develop downdrafts, we will compute the entrainment rate based on the magnitude of the downdrafts at the prior time step. And so the entrainment length scale is a function of the height of the plume ensemble and the downdraft magnitude, and that is required in order to simulate from shallow to deep convection using this model. There's also a per plume approach, which is new, and where instead of having the ensemble see the same entrainment length scale, each plume will compute its own entrainment length scale based on the plate of that plume at the prior time step, not the height of the maximum height of the ensemble, that plume. And similarly, its cold pool will be determined by its downdraft of that plume at the prior time step. So this is just showing the impact of these per plume mods in a SCAM case. And this is the LBA case. On the left is the top of the plume ensemble versus time. The LES is the dotted line. And I will just say our blue is our standard Club MF. And so you can get, you can sort of reach the height of the LES solution. However, your precipitation rates are very large compared to LES. Whereas with the per plume methods, we have a more diverse ensemble where you have more shallow members in your ensemble. And so as a result, you actually get the same profile, but you can get more realistic precipitation rates. So now I'm going to switch gears for a second. So we developed Club MF in a CAM tag that's about 2 years old, CAM 63041. And we're now up to CAM 63132 that we're using for CAM 7 evaluation. And we decided that it's worth our time to try to merge our code base up to what we're using in CAM 7 so we can kind of be neck and neck with CAM 7 and compare our solutions against theirs and provide an alternative, potentially. This was kind of a lot of work. You have to do a lot of git commands, and it's just monotonous trying to manually fix merge conflicts. And so I thank Ben Stevens for his assistance with this. The scientific validation was even more challenging because the solutions changed a lot over the course of these 2 years. And at this point, Club MF's problems and CAM 7's problems were the same. The solutions changed over the last 2 years and we had to figure out why. And so this tag audit that I talked about on Monday really provides help with those two avenues, those two problems we were having. The main thing that came out of this was that we found out that in the new club externals in 059, they turned off downgradient diffusion of theta L in total water by club. So it kind of slipped by us that in prior versions of the model, or prior to 059, that this additional downgradient diffusion was happening on top of club's prognostic turbulence. And so when we were running club MF in that code, there was kind of triple mixing going on that we didn't really intend. And it was actually diffusing our mass flux solution as well. And in hindsight, it doesn't seem like that was appropriate. And so even though that was a mistake, I'm glad we figured it out and we did this sort of tag on it to figure that out. So just to show what the solutions look like in old code bases versus the new ones, this is the total precipitable water in 2 observational products and some 10-year AMIP runs. CAM7 old here on the left, CAM7 new on the right. And so as I showed on Monday, the solutions got a lot drier over the course of those 2 years. Same thing with Club MF. Club MF old versus Club MF new. You can see that the contours are not as pink. It's not too different from CAM7 new, except for that this northern flank of moisture is kind of moved westward into this box here. And so technically, if you average over this box is moisture, Club MF new versus CAM7 new. The per plume mods actually moisten things up even more, which I'm going to go into in a second. I'm going to go into now. So these are averages over that box in the West Pacific, just looking at DJF, and a couple of those AMIP experiments. So we're looking at CAM7 in gray and CAM7 RD. So that's when we reverted the diffusion on and back on, and I include that because that is a candidate for CAM7. And the thinking here is that our mass flux plumes can kind of do what that revert diffusion was doing in prior code bases. And so it's actually an opportune moment for mass fluxes to step in here. So all the Club MFs are the Club MF standard is this cyan thick line, and then the purple and pink are the per plumes. You can see the tropical atmosphere is warmer and definitely in the mid to upper troposphere. These are, I guess I didn't say, these are actually biases with respect to ERA5. Okay, so that's the reference we're using here. And so if you look at the moisture differences from ERA5, the CAM7 solutions are all over here, and so the Club MF does moisten things up in the middle to upper free troposphere. The per plume mods actually do moisten things up at shallower layers, which is what we saw in the SCAM experiments. And that's actually, this blue line is revert diffusion, so that's also what revert diffusion does at shallows and moistens those shallow layers. If we come down to the tendencies, these are the ZM tendencies, so there's only 2 lines because we have only 2 runs with the ZM on. ZM, and these are moisture tendencies, detrains a lot around 5 kilometers, around the mid-troposphere. And if you compare it to Club MF, these are the Club MF tendencies, so including Club and MF for total water. In CAM, basically there's a lot of cancellation between PBL mixing from Club and deep convection drying. And since the MF plumes are added in here, you don't see, they sort of offset each other. And so let me try to get rid of this offset between ZM and RTM by adding them together. And now we're looking at all convection tendencies. And you can see the detrainment by the Club MF is much higher. And the detrainment by ZM is very pointed, and it's at these lower levels. And it's a very unique feature of ZM. One would think you would want sort of more equal spreading of detrainment across layers in the upper troposphere. This is the convective heating. So it's not too different from ZM, except for once you start going up into the upper troposphere. So all this warming up here in the Club MF code is really due to condensing this moisture. So it's the energy, the additional moistatic energy due to this moisture flux. These are the mass fluxes. So ZM mass fluxes are in the gray and the blue here, and you can see this is why detrainment occurs at sort of 5 kilometers, is you have this rapid reduction in mass fluxes with height there in ZM. Whereas Club MF mass fluxes sort of extend, decay more gradually with height and extend to higher levels. And so there's some obvious benefits of going to Club MF. The view of tropical variability is not as clear. So I'm showing here some wave frequency spectras, symmetric modes. So these are raw, these are not scaled by the background noise. And then these are Hofmeiler lagged regression coefficients of precipitation from the Indian Ocean over the maritime continent into the Central Pacific. So this is Camp 7 here, and it looks okay. There is propagation. It's obviously muted compared to observations. I will note you can get a very different answer if you couple with the ocean. So I'm just gonna leave it there. And then these down here are 4 iterations of Club MF. And I would say that there's 1 or 2 of them that are quite competitive with Camp 7. This one here and maybe this one here. The negative correlations kind of almost pop a little more than the positive correlations. And you do, in some cases, do get sort of a greater Kelvin wave activity from Club MF. So it's a bit of a mixed bag when it comes to tropical variability. I think that there's probably missing processes. We have not experimented with the gust parameterization that Meg talked about. And, the mesoscale heating and momentum transport from Jack and Mitch would be something to think about looking into. Just want to see how long I've been talking for. Probably too long, but we have some cancellations. But this is the last slide. So the last one is, I want to talk about coupling Club MF to aerosol cloud processes. It turns out it's very important. So in Camp 7, the way that the convection schemes are coupled to the aerosol processes is you have 2 processes. First of all, you have aerosol activation, which is liquid forming on aerosols, and then ice nucleation, which is heterogeneous freezing onto aerosols. And in both of those, you need an updraft velocity to solve for those activation and nucleation rates. And that currently is, one example of where it's drawn is it's drawn from this variable down here, which is the vertical component of the club TKE. And when you turn on the mass flux plumes, this decreases. More generally because the mass flux mixing relieves any sort of instability for club to operate on. So you generally see when MFs are active, club goes down. So you'll also notice that the ice numbers go down too. So it turns out that this term is very important for controlling ice nucleation. Just emphasizing that. But in addition to, if you're going to use an updraft to compute the sort of activation rates, you should use that updraft to transport the aerosols too. So there's also diffusive transport of aerosols by club. And then there's a deep path for activation and ice nucleation, where the ZM scheme will actually transport the aerosols, do scavenging, and it is my understanding that the updraft mass flux participates in activating and ice nucleation. So we're evaluating different methods for incorporating the MF blooms into these processes. To show their importance, this is the annual mean shortwave cloud forcing from Ceres. Here is Camp 7 over here, so it looks decent. I always get that nice transition from stratocumulus to cumulus. And you get these nice reflective clouds, cirrus anvil clouds in the West Pacific. If we go down to Club MF, we get that transition from stratocumulus to cumulus, but something is missing here. And that's mostly because our ice numbers were lowered because they're dependent on that W prime squared club quantity. So if you look at the per plume methods, they're pretty much the same. This one looks a little bit better. But when I decided to go ahead and try to do something about it, so I did estimate the updraft velocity from Club MF and use it for the activation, I got this answer down here. And so now we're getting larger nice number concentrations sort of in those Cirrus anvils in the West Pacific. And, you know, this is just something you really have to make sure you pay attention to when you implement a convection scheme into CAM, because the ice number concentration is just as important for cloud brightness as mass concentration. So that's all for now. Take any questions or comments you have.
Julio.
So the vertical velocity from ZM was never included in aerosol activation parameterization, right?
I think in CAM 6 that's true.
Okay.
Between CAM 6 and CAM 7, we turned on this convective scavenging routine. And now the way that the aerosol, and it changed the workflow of how aerosols interact with the deep convection scheme. Took it out of end drop and put it in the wet deposition scheme. So I'm kind of not sure right now. I'm trying to figure out whether it is actually activating aerosols.
Mitch.
Interesting. Do I get this right? You said that your cloud depths are higher, in fact, with in your calculations than in ZM?
Yeah, I didn't say that, but I think that's apparent.
It seems, I thought that was one of the, because I thought it was the opposite way around. Yeah. But you're in fact, convection is higher. Is that
Yeah, I
correct?
would say the turquoise and the pink and the purple, if you look at the cloud,
It doesn't cut off at 500 millibars.
I'm looking at these ice clouds here.
Well, that's important as well, yeah.
That are definitely higher than the gray line.
Yes, I see.
And I do attribute that to higher detrainment.
Yes. So, and that's an interesting point here. The optical variability, the positive effect that Jack and I have found is actually with some of the top level, the heating upper levels and cooling lower levels. It's the mesoscale heating really that's generating the Kelvin waves. And the heat, that heating is an ensemble, an effect of an ensemble of cumulus. So in fact, what we're putting, the reason we're getting better Kelvin waves and other things like MJO is because of that top heavy heating. Mm-hmm. And it's the mesoscale bit coming in. And this is an extremely interesting business, actually. It's actually in much better shape than I thought it was, compared to ZM.
Yeah, I mean, I can think of a way to couple your baroclinic mesoscale heating to the depth of the MF convection.
Yes, exactly. And the anvil region is very important.
Mm-hmm. Yeah, and I mean, I think that there is some of that heating because you're providing that energy up there.
Yes.
But that's just grid scale condensation.
Ah, that's grid scale condensation. I see. Okay. Okay. So, but the mesoscale organization, if you like, has put it in a lot of energy too.
Yeah, I would say it's not.
And momentum too. The momentum transport is the opposite sign. So.
I think it's
It's
important.
extremely interesting. This. Yeah. But I'm more encouraged than I was hoping. I thought I would be. Yeah.
Well, good, Mitch.
That's okay. I didn't mean it to be a negative statement.
No, that's, I take it as a compliment.
Go ahead, Brian.
Going back to the aerosol issue, you were pointing out the issues in the kind of the upper troposphere in the tropics with aerosol activation for ice particles.
Yeah.
I feel like, and you tell me if I'm wrong about this, but I feel like the important thing about convective activation of ice is more near the mid-troposphere where you transport the aerosol up, you get activation, you release the latent heat, and that actually produces convective invigoration. And then when you get really high up into the troposphere, you shouldn't worry too much about heterogeneous nucleation so much as homogeneous nucleation, which should be taken care of by pumas.
Yeah, I mean, that's supposed to be the coldest region on Earth up there, in the upper troposphere of the tropics, so I guess you're right, it should be mostly homogeneous freezing, but this relationship in the model is these are very tightly coupled. W prime squared and club up here with this ice cloud. I mean, I've done runs where I've decoupled these and the reflectiveness goes away. And so maybe I just don't understand how this W prime squared is feeding into the activation, dice nucleation.
Yeah, or maybe the interaction between the heterogeneous and homogeneous freezing processes that is broken.
Yeah, there's so many possibilities and I need to take a closer look and yeah, you raised some good points I'll need to look into.
Sean?
I had a question from, like, near the beginning, you were talking about this entrainment length scale. I had sort of two interrelated questions about it. One is, this talks all about Pryor's time steps. One was, how do you initialize it to start with? And the second is, when you don't have much convection going on, do any of the plumes turn off so that you need to like reinitialize? Or are they like still present, just like shallow and weak? And so you have persistent state across like relatively.
I think that's true actually. Like at the very least, you'll have very frequent mass flux plumes in the first 3 levels. You know, that are kind of, they're active, I would say 90% of the time. You know, and there are times when it's not active as well. And so it's something I'm kind of keeping my eye out for. So if you look down, so here I actually look at a lower slice, so just 6 kilometers to 0, and down here you can see the convective mass fluxes. And I extended the y-axis so you can see, you know, the xenon mass fluxes are underneath here. So it's, this is mostly a frequency effect, but it's there. And I do have to watch out for it. I've had to, so I'm keeping my eye on it. It does, so we have a paper, monthly weather review, that looks at these in single column cases, and those lower levels do help mix things like shallow convection dicoms profiles, and they're not deteriorating the solution, so they seem to be helpful. It also ends up reducing the amount of the club turbulent fluxes because there's just less gradients to create large prognostic fluxes.
And the plumes are not transporting momentum in the, like,
Not
in this
here.
case?
Not, I have that option. It's not fully developed and it's not on here.
Okay. That's not like a positive or negative, I'm just trying to wrap my head around it.
Yeah, no momentum transport, just heat and moisture. And to your other question, you know, how do you initialize when you're basing things off the previous time step? Well, we have a sort of minimum entrainment length scale that we activate if it hits there, and so we just initialize it with the minimum value. And the convection seems to grow in single column models fine, so.
Okay.
Kind of works itself out surprisingly.
Rich?
So the West Pacific is a very, you know, it's the strongest force region in the tropics, and I'm wondering, problems often come with, problems are greater in like the East Pacific, which is like a marginal. If you look at reanalysis in the East Pacific, they don't agree very well. Here they agree. Most models get about the right response. I wonder if you've looked at other regions, because I suspect in somewhere like the East Pacific, ITCZ, you'll get a much different response between all these, particularly ZM and whatever your latest and greatest is.
Yeah, I think that I was pretty happy with, so we spent a lot of time on the dicons to Hawaii, marine stratocumulus to shallow convection transition. So not East Pacific proper, what you're talking about, but looking at intermediate, sort of not as strongly forced regions, and we got it. We were really happy with our results, and then we merged up. And I will have to say that in this simulation, I was not happy that the MF plumes are not very active over the Hawaii region. right now. So, we work, so I need to look at that and recover our old solution. But what I'm saying is you can get it to do sort of mid-level shallow convection. At the very least, we can get it to do what that revert diffusion was doing, where we're sort of helping mix things along the way. So it's possible, and hopefully probable.
One more. This business about seasonal variability. The Indian Ocean is very different, of course, because of the monsoonal setup. Have you looked at the Indian Ocean separately from the Western Pacific, or do you take the whole lot, add it together?
I would say I kind of have not looked at the Indian Ocean specifically.
It's a very different, climate really, seasonal variability, and it's very interesting as well. And of course, that is the maritime continent. So there are really 3 different regions.
Yeah, and you can kind of do like those lag regression hot-miler plots in latitude for the Indian monsoon, is what I understand as well. So maybe that would be a good metric to try.
I think those 3 things might be interesting in a seasonal to larger scale kind of, framework.
Yeah.
Because the physics and dynamics are very different in the ocean from the Western Pacific. In detail.
Good point.
Alrighty, thank you, Adam. Next up is Kyle. You're going to talk about diagnostics to assess the impact of club parameters on global and regional metrics in K6.
All right, thanks.
And I know this works. If you push the top here, you can sometimes point. Maybe just use the laptop.
Yeah, sounds great. All right, thank you. All right, so I appreciate the opportunity to come visit NCAR and present on some of my ongoing PhD research at Penn State with my advisor, Colin Zarzicki. So I'm funded under the other CPT, the Momentum Flux CPT. And as part of that, the main goal of my work is to better understand how some of these club parameters are introduced in the TAOS code and in prognostic momentum flux affect certain aspects of the global and regional climate. So I am using a sensitivity analysis where I'm perturbing some of these club parameters and then seeing how some of these global and regional metrics change. And I'm really interested in getting sort of a better understanding of the physical mechanisms that are at play. So I've created some diagnostics that help us look at that. I'm going to share some of those here. So as I mentioned, the main goal of my work is to better understand both how and why some of these club parameters are influencing various aspects of the global climate system. So I'm running club with prognostic momentum flux and the TAOS code turned on, and I refer to this as club X. And a prior study of mine showed that certain TAOS code parameters were influential in modulating the structure of the boundary layer in extreme weather phenomena like tropical cyclones. And so I'm really interested in seeing how some of these parameters then influence the modeled climate over longer timescales. So to do this, I run a simple parameter sensitivity analysis called the Morris one-at-a-time method. And the key to this method is that we're running a bunch of simulations, and from one simulation to the next, we're changing the value of only one input parameter, and we're keeping everything else constant. And again, the main goal is to get a better understanding of some of the physical mechanisms that play. So the goal of this work isn't to necessarily provide an optimal set of parameter tunings in Club X. Rather, we're interested in getting a better understanding of which parameters are more influential compared to others, and it can serve as a basis for providing more of a physical understanding of some of these parameters and more of a detailed analysis of them. So I'm running this sensitivity analysis on many short-term initialized hindcasts, and I'm running CAM6 over 3 days. And this is similar to a methodology from Sean et al. In 2018. They did this with E3SM, and interestingly, they found that running sensitivity analysis on 3-day simulations actually provided a lot of useful information for sensitivity for 10-year simulations. So we want to see if we get the same kind of result. So I'm running in beta cast mode, and essentially this is a setup where we are initializing the atmosphere with ERA5 initial conditions, and we have prescribed sea surface temperatures and sea ice. And I run land model with the data atmosphere to spin up the land for 12 months prior to each initialization. And I am perturbing 17 parameters. Most of these are club parameters, including parameters that are in the Taos code and also prognostic momentum flux. And I also have some microphysics parameters in there as well for reference. And the way the Morris method works is you perturb each parameter one at a time. You do this 10 times for 10 different initial combinations of input parameters. And along one of these paths, you change each input parameter value one at a time. So this results in 180 unique combinations of club X parameter values. And I run, for each combination, I run the betacast 24 times with 24 different sets of initial conditions. And this is a better way to sample different times of the year, different synoptic setups at initialization. So for each month of the year, I select 2 years randomly between 2010 and 2020, and then I initialize the hindcast at 0Z of the first of that month. And this results in over 4,000 total 3-day simulations, and one of the reasons why we stick to 3-day simulations is to keep this relatively computationally effective. So from the sensitivity analysis, we have several metrics that we can explore. So this is a heat map of the average magnitude of the response of each of the output metrics, which is here on the horizontal axis, to these 17 club parameters on the vertical axis. Darker colors imply that changing the input parameter produces a relatively large response in the output metric. And these are for several boundary layer metrics averaged over the southern storm track. So that's from 40 degrees south to 70 degrees south over all longitudes. And what I'll note here is that for my diagnostics, I have these same kinds of heat maps for various output metrics, cloud radiative, different synoptic quantities, and I also average this over different regions. So here over the southern storm track, I am going to highlight this column in the middle. This is Taos surface, this is surface wind stress. So this column here represents for each input parameter the relative response in the surface wind stress. And I'm highlighting C inverse Taos shear, which is up there at the top. This is one of the input parameters that was introduced in the Taos code, and it affects the amount of turbulent eddy dissipation due to vertical wind shear. And you can see that for most of these boundary layer metrics, including surface wind stress, C inverse Taos shear produces a relatively large average response in surface wind stress. Now this heat map here is showing the direction of the response. So this is the frequency with which increasing the input parameter increases the output metric. So for example, if we look at the intersection between surface wind stress and C inverse Taos shear there, the deep blue implies that in our analysis, every time we increased C inverse Taos shear, we decreased surface wind stress. That's how you would interpret that plot. So as I mentioned, we can do the same kind of analysis, but for different regions and different metrics. These are cloud radiative metrics now over a tropical band. And I'll show here short-wave cloud forcing on the left. And one of the parameters that's relatively influential is club C8. This has been shown in various sensitivity papers that C8 is relatively influential for low cloud fraction and for short-wave cloud forcing. And what we see is that in our analysis, when we increased club C8, we almost always decreased short cloud forcing, or thought of another way, we increased low cloud percentage. So now, one of the cool parts of this Morris analysis is that since we are changing each input parameter one at a time, we can collect all of those instances where we only increased C inverse Taos shear, and we can do a before and after analysis. So what I'm doing here is taking the 240 instances where we increase C inverse Taos shear, averaging these fields, and then comparing that to the 240 simulations before we increase the inverse Taos shear. So I'm showing here on the left, U-bot, so this is the model level, this is the wind speed at the lowest model level, and then on the right, that's surface wind stress. So the blues here imply that when we increase the inverse Taos shear, we are getting a decrease in low level wind speeds and also in surface wind stress, as you can see there. Over the storm track regions, both hemispheres, but especially over the southern storm track, we're getting a reduction in low level wind speeds and surface wind stress when we increase the inverse Taos shear. So now we can go a little bit deeper and start to look at some of the vertical profiles that are relevant for vertical turbulent mixing and see why maybe we're getting some of these responses in low level winds. So what I'm showing here is a distribution at each vertical level of the different output metrics before and after we increase the inverse Taos shear. So the blue here is the distribution of, in this case, eddy dissipation due to vertical wind shear before and after increasing C inverse tau shear. And this is the term here that appears in the Tau's code formulation for turbulent eddy dissipation or inverse tau. So this physically is representing the breakup of larger turbulent eddies into smaller turbulent eddies in the presence of vertical wind shear. So C shear here is C inverse tau shear, that's the coefficient we're changing. And as we would expect when we're increasing C inverse tau shear, and again, this is average over the southern storm track where we expect there to be higher vertical wind shear, we are getting an increase in this shear-related eddy dissipation. So if we are increasing this component of eddy dissipation, so this is one of the values in the sum of inverse tau, when we look at the eddy turnover time scale, which is just tau, we expect there to be a decrease because we're increasing the amount of eddy dissipation. And that is indeed what we get after we increase C inverse tau shear. And then tau then appears in the formulation for prognostic momentum flux in this pressure damping or returned isotropy term. And when we get a decrease in tau, we expect this term to increase. That's sort of acting as additional damping in the budget for momentum flux. And indeed, that is what we get. So if we look at total vertical momentum flux, with these changes, we do get a slight reduction in vertical momentum flux in the lowest model levels. We also get a reduction in TKE. And then we get a response in wind speed in that we have an increase in vertical wind shear at the lowest model levels. We're getting an increase generally above 200 meters and then a decrease below. And we hypothesize that this change in vertical wind shear with less vertical turbulent mixing, that is what is resulting in the lower wind speeds at the lowest model level, and then that's feeding back into the surface wind stress. And again, I want to note these are average over the southern storm track, and these are for the 3-day simulations. So now we can then test to see if these results we get for 3-day simulations also appear for longer simulations. So for an illustrative example, let's say we want to have two different outcomes. Let's say we want to decrease surface wind stress over the southern storm track, which we just talked about, and we also want to increase short cloud forcing, or dim clouds. And I'm not suggesting that this is what we would want to do operationally. This is just an illustrative example just to see how we can maybe use some of these Morris sensitivity results to get changes in the global mean climate. So the Morris method highlights several pathways towards achieving this. So first, we could increase the inverse tau shear. That was shown to decrease surface wind stress for the 3-day simulations. And also, we found that decreasing C8 will increase short cloud forcing or decrease cloud fraction. So we chose these parameters because the Morris method showed us that each of these parameters has a relatively large influence on one of these outputs, but has a relatively lower impact on the other metric. So we run two 10-year FCOMSET simulations, one baseline and then one where we are making these two experimental parameter perturbations. We want to compare the before and after and see if we get the responses that we're expecting. So this is a difference between the perturbed simulation and the baseline simulation. This is for short cloud forcing, and this is the response we were expecting. When we make these changes, we are getting an increase in shortwave cloud forcing over the tropical region. But we are getting a response in surface wind stress that we weren't expecting. Before, when I showed the plot, that same plot for the 3-day simulations, we saw a very large swath of blue over the southern storm track. But here, we actually see the swath of red implying that surface wind stress is actually increasing, which is different from what we saw with the 3-day simulations. So in a few slides, I'll go into a little bit of our analysis of why that might be happening. But first, I wanted to just put a bow on short cloud forcing and say that we're getting the physical responses that we're expecting. So when we think when we change C8, when we decrease C8, we're getting a decrease in low cloud percentage. And C8 is a coefficient in the damping of W skewness, which is shown there on the right. So we would expect if we're decreasing C8, we're getting less damping of W skewness, and that's going to result in an increase in W skewness, which is what we see there. And then with a higher W skewness, we expect there to be more of a cumulus regime versus stratocumulus regime. So we think this makes sense. That's why we're getting this change in low cloud percentage when we change C8. Now, going into the surface wind stress, we notice that when we make these changes, we are getting this swath of actually increases in wind speeds at the lowest model level. And spatially, that coincides pretty well with this increase in the surface pressure gradient. And we actually see that throughout the column over the southern storm track, we're getting this synoptic response where we're getting increased wind speeds in this area And we're trying to understand exactly why this sea level pressure change is occurring. But I think this is just to illustrate that there are some nonlinearities that are at play here that we maybe didn't capture with the 3-day simulations that are occurring with the 10-year simulations. We're trying to untangle a little bit of those. So I will just go into these vertical profiles again and show that we're generally getting the same responses in eddy dissipation and in pressure damping that we were getting for the 3-day simulations. We're not really getting as much of a change in momentum flux, and I have a few thoughts as to why that's potentially happening. We do get a reduction in turbulent kinetic energy, and then we do get this increase in wind shear still, but with the 10-year simulations over the southern storm track, that increase in wind shear isn't providing us with the decreased wind speeds that we were seeing before. That is occurring over other regions of the globe, but not over the southern storm track. And again, we think that perhaps with this change in the pressure gradient, we're getting a change in the geostrophic wind, which could be sort of acting as playing a role in how the wind field is changing. But that's something that we're still trying to get our heads around. This is a relatively new result. So let's show my main takeaways. I think the 3-day hindcast can be very useful for providing information about parameter sensitivities for certain metrics, like, for example, cloud fraction, short cloud forcing. And I'll note that the paper we were basing this analysis on, Sean et al., they were mainly looking at parameters like C8, gamma, C11 that were relevant for cloud radiative forcings, but they weren't necessarily looking at, obviously, these Taos code parameters. So I'll just note that for other fields like low-level wind profile, surface stress, perhaps these 3-day hindcasts aren't sufficient to capture some of these nonlinear actions that are occurring. So future work, trying to better understand some of the physical mechanisms driving these responses to sea level pressure, because that seems to be playing a role here. We're looking at things like wind turning, cross isobaric mass flux, and just changes in the general circulation. So I'll just also note here that I have this club diagnostics page where I have all of these heat maps for different regions for these 3-day simulations. I know Ben and Vince have been using these results, so those are available if anyone's interested. Otherwise, if there are any questions. Yeah.
Questions, Sean?
I was just curious for this shear-related results, if you looked at diurnal cycle, or if you have an idea of where if this parameter mostly like affecting convectively stable boundary layers, or like.
Yeah, I haven't looked at that specifically, but I could potentially leverage some of the 3-day simulations I have, because I have more output at a higher temporal frequency. So that's something I could potentially look at, but that's a good suggestion.
You know, this is an increase in wind shear. That's a particular interesting thing, because that's very much related to the cold air outbreaks behind mid-latitude cyclones. And particularly in the places you're looking at. It also happened to work in the tropics, where you got trade wind parallel lines. But that's also increased wind shear. So you need to look at the organization of convection.
Okay, yeah, that's a good suggestion, I appreciate that.
Dave?
I was wondering whether or not there's any plans to try to apply this to the CAM7 version and try to use this technique to do some little bit of a tuning or calibrating the CAM7 if there's some problems with the CAM7.
That's not something that we've discussed specifically, but that would be really interesting to potentially do. And I think like this methodology could be very useful for doing something like that.
It's true that this run a traditional PP with we call it Club X, or the Club Towers. But we haven't really looked much into it yet. Any other questions? Right.
Well, yeah, I mean, it just seems like here you could you're essentially running a PPE, but with only 4,000 years of simulation, right? Was it 4,000 years?
It's 4,000 like 3-day simulations.
4,000, yeah, so not even that,
Yeah.
much shorter than that, yeah, so.
We ran 3 years. So.
Yeah, so you could go through, do it a few times, and yeah, compared to the PPE, which was a big undertaking.
And I will say that I have compared some of my results to some of the preliminary results from the most recent PPE, and at least for the cloud rated metrics, like again, short cloud forcing and looking at like C8 and some of the microphysics parameters, like this methodology provides very similar results. But I think there are certain other parameters that we're looking at that maybe weren't covered in that are maybe a little more problematic. But they have compared fairly well for some of the parameters we've looked at.
All right, thank
All
you,
right,
Kyle. So next up is supposed to be David Mitchell, but I do not see him in here or online. Just check one more time here.
It's booking every year.
Wow.
Until I
Yeah,
remember
for-
back,
for-
yeah.
Yeah,
Like
for
20
200
years.
years.
Yeah.
So Dave, if you're online under a different name, please speak up.
Yeah.
I think that's the reason.
And yes,
Otherwise, Helen, would you be willing to give your presentation now? It's almost unscheduled.
He told us to ask questions.
It's supposed to start at 10, so yeah. See this thing recovered? Oh, it recovered. Okay, so if you want to, you can use this. You can
And
point
point
at
at
the
the
screen,
computer.
or you can point
Okay.
up here as well. So quick, Caitlin Loftus is next up. She's going to talk about a flexible Bayesian approach for parameterization of warm microphysics. Okay, take it away.
Hi, everybody. Thanks. So yeah, my name's Kate Loftus. I'm at Columbia working with the LEAP Science and Technology Center. And today I want to talk about some work to build a framework for microphysics parameterization that's both flexible and Bayesian. And so to start, the name of this framework is BOSS, which stands for Bayesian Observationally Constrained Statistical Physics Scheme. And the idea is to flexibly configure microphysics parameterizations via Bayesian inference. And just to give you a sketch of what kind of do I mean by flexible and Bayesian, here's kind of how BOSS might approach assembling the building blocks of a parameterization. So by building blocks, we can think about what are our prognostic variables, what kind of functional forms are we using for different temporal and spatial derivatives, and our parameters. So for prognostic variables, for BOSS, we're thinking about different moments of the drop size distribution. So this could be kind of traditional two-category cloud and rain moments, or we're also kind of in work led by Sean Santos looking at single liquid category moments where we can get better information about higher order effects that traditionally can't be seen. For our derivative functional forms, we're looking at physics-informed power series process rates, and we have adjustable levels of complexity. And then together, this kind of allows us to have a flexible structure because we can adjust both our functional forms of our derivatives and also our prognostic variables. And then finally, we constrain parameters via Bayesian inference. And so today I want to talk about development of BOSS in 3D models. Specifically, we're looking at LES and the atmospheric component of Earth system models. Our idea is to kind of work in LES to assess different structural ways to set up microphysics parameterizations using as constraints kind of more complex microphysics schemes. So like bin schemes or Lagrangian particle schemes where we can kind of resolve the cloud dynamics. And then we want to use what we learn in LES to see what kind of structures we should test in our system models where we can kind of constrain parameters via satellite observation, historical record, and then as Marcus kind of was alluding to yesterday, different single column experiments. And so I'll just start off by saying, like, what have we done so far towards these 3D development? So first, we've implemented versions of BOSS in LES and then also in CESM. So Trude Eidenhammer has put in BOSS to the most recent development branch of PUMAs. And then also Poland Ma, along with Hugh Morrison, have been working in E3SM. I'll just quickly show some results from BOSS and E3SM. Here we kind of have like a standard structural configuration with boss parameters coming from a 1D kinematic driver constraint. The top panel is showing shortwave cloud radiative forcing from series, and then the two bottom panels are showing kind of an in development E3SM standard version, and then the boss results. We can see that the boss results are kind of running, and they actually look quite a bit better than the E3SM standard. But the main thing I want to talk about today is development on what Marcus was discussing yesterday, which is kind of making this Bayesian parameter inference component of scheme development possible in kind of expensive 3D models with machine learning. So I'll basically just sketch what we do. So we want to use kind of direct Bayesian inference, or MCMC, to find optimal parameters given some kind of constraint sources based on some kind of key metrics and uncertainties. If we were to do this in the actual climate model, it's way too expensive. So instead what we do is replace running the climate model with a machine learning emulator, which is much cheaper, and we train this machine emulator with a much smaller set of different parameter sets. And so today I want to show some results focused on LES, where we're constraining 16 different BOSS microphysics parameters using a more complex bin microphysics scheme. We're doing this with a CM1. We're looking at a marine stratocumulus setup, and our constraint source is just that same model, same LES with just more complex bin microphysics. We are using as kind of key metrics different spatiotemporal averages from the end of the simulation, and we account for uncertainty both from dynamical variability in the simulations as well as emulator uncertainty, which is an extension kind of developed after the GIS GCM tuning. And then finally, we're using a special type of neural network called a random priorized network to emulate the outputs from the different BOSS runs. And in case I lost you in all of that detail, basically the idea is we're going to constrain 16 parameters from the microphysics scheme in LES using a more complex bin microphysics scheme, which has about 20 times more prognostic variables, and also the calculations of each process rate are much more detailed in this scheme. And so I'll show results from kind of two experiments. The first is we perform this Bayesian inference using a constraint from 6 different aerosol conditions spanning from raining to not raining. We have 850 different parameter sets of BOSS to train our emulator. And so here I'm just going to show one metric that we use to kind of evaluate the performance of the different BOSS parameter combinations, but for the sake of time. So here I'm showing, mean surface rain rate for the last 2 hours of the simulation as a function of background aerosol mixing ratios. So here in black, I'm showing the bin simulations, and these standard deviation or error bars are coming from different dynamical realizations. And now I can plug in different parameter combinations into the machine learning emulator to predict how BOSS would predict this same mean surface rate as a function of different parameters. So here I'm showing now as a function of this aerosol mixing ratio, the solid line is showing kind of the predicted value of the emulator, and this shading is showing the uncertainty. And I can just kind of select different parameter combinations, and you can see we can evaluate how each parameter combination is doing versus the bin scheme. And then now I'm going to layer a bunch of different parameter combinations all at once. So these are coming from our prior parameter sets. We have drawn 500 different samples, and this is showing kind of, and the prior is informed from kind of direct fitting of the process rates. We see that we can kind of span the bin results, but any individual run isn't really capturing what's going on with the bin scheme. In contrast, I can show what happens when we draw from the posterior. We can see that we're matching what the bin scheme is predicting. And in general, we see that as long as this is kind of structurally possible, we can see good agreements between our posterior parameter distributions and the bin metrics. And also, so that was all using machine learning. Here, we're gonna actually put these parameter combinations back into the full LES simulation to just check what's happening. So now I have mean surface rain rate on the y-axis, time on the x-axis, and each panel is showing a different aerosol value. This in black is showing the different bin runs under different random initializations. And we can see that the BOSS runs, so these are coming from our posterior, continue to show skill in the full LES simulation. I could also look at how the liquid drop mass flux is changing as a function of altitude. And again, we have 3 panels showing different background aerosols. We see the variability of the different bin runs. And again, when we look at the posterior from the BOSS simulations run back through the LES, we see kind of good agreement with the bin metrics, suggesting that this workflow is doing what we think it is, and it's not just machine learning telling us we have something that looks good. And I'll just quickly show some work in progress, a second experiment where we have much more diverse environmental conditions. So we're now constraining BOSS with 135 different conditions instead of 6. And in addition to background aerosol, we're also varying water and temperature profiles. And these different plots are just kind of showing different realizations of liquid water path. We're spanning a much larger space of cloud structures, even though these are still all stratocumulus runs. And so here we have a much more abstracted view of how this kind of tuning process is working, but I'm just showing here distributions of how the BOSS error with respect to the bin results. So for each environmental condition and each metric that we're using to evaluate BOSS's performance, we run 1,000 parameter sets for both the prior in black and the posterior in purple. And we can see that the posterior, we've greatly kind of narrowed the error, and we've also recentered it around 0. And this is just a Gaussian curve for reference. So this seems to be showing promise that we can perform this fitting beyond just a limited set of conditions. And with that, I will just quickly summarize. So BOSS is a flexible Bayesian approach for parameterizing more microphysics. We're working to extend this framework to 3D models. A key development feature that we need to enact in order to do this in expensive 3D models is this machine learning enabled Bayesian parameter inference, which is a quantitative method of interest kind of probably beyond this workflow, where we can kind of select parameters, characterize parametric uncertainty, and also start to distinguish parametric and structural error in parameterizations. And I showed an example of a successful implementation of this methodology for cloud microphysics parameterization in LES. And so with that, I can take any questions. Thank you.
Questions? Adam?
I guess just because we've been talking about ice nucleation activation, that's not something that you're experimenting with. You're just looking at the microphysics process rates for like autoconversion?
Yeah, right now we're just looking at warm microphysics. I think ultimately, a few years down the line, we would extend that to think about mixed phase and ice microphysics. But yeah, for now, our focus is kind of on the simpler warm cases.
And I am new to aerosols, but activation is a warm process. Aerosol.
Yeah, I think like often people will say activation to describe warm.
But it must be occurring in your model because you're looking at things versus the amount of background aerosol. So there is aerosol.
Yeah, there is aerosol activation. So like when does the liquid drop become stable to, it's a function of like what it's composed of and size. That's in the model.
Thanks for bearing with me.
No worries. Yeah, there's all those microphysics jargon.
Dave?
I have a non-atmospheric scientist question. I'm trying to understand where BOSS sits relative to PUMAS, and you said you put it into PUMAS, but I don't.
Yeah, so
Can you sort of explain?
basically, there's been some development in PUMAS recently, which enables different selection of different warm microphysics approaches. So basically, so I think the project kind of motivated that. They're trying to put this machine learning emulator into CAM. So basically, we did the same thing except with BOSS as an option.
And then BOSS differs from the whatever the warm microphysics in what way is it?
Yeah, so the implementation that's in there now is basically quite similar to the MG approach. There's like, I think one process that's not in MG, which is cloud self-collection. But kind of the main development would be towards first getting kind of this kind of parameter inference set up to work in kind of mixing like single column CAM and then also, like full global runs. And then also we want to implement like much more diverse structural parameterization. So right now with E3SM, we've put in like a very different structural approach than what's currently in PUMAS. But that's kind of a lot of development work because all of the other, so like club and the radiation all expect certain things out of the microphysics. So that development process is a lot longer than kind of keeping all the same prognostic variables and just tweaking the process rates.
If you want to know how this differs from like MG or what PUMAS is doing before, it's partly there's one extra process and a few more like terms to some of the equations, and partly it's that there's a lot of parameters that just nobody's bothered or hasn't systematically tuned from the previous versions that are now actually being optimized using this framework.
But in general, it sits sort of in between like a full ML approach that's sort of fully structurally flexible and a traditional parameterization scheme that's where a lot of the structure is sort of baked in. So there is some flexibility, but it still happens within a sort of physical framework. You still have physical processes. There's still some physical assumptions on how the process rates and size distribution moments should work. So somewhere in between the fully data-driven and the fully just sort of physically hard-baked approaches.
What would you call the work that Andrew's doing on simulating the warming, the fully data-driven version?
Yeah, I'd say that's closer to fully data-driven. Yeah.
Just a clarification on this exact thing is, I'm wondering, with the BOSS implementation, does it eliminate the need to have an auto-conversion scheme in the global model?
So it depends on maybe I could just quickly go back to like this kind of conceptual setup of building a parameterization. So in order to get rid of auto-conversion, we kind of have to adjust like what prognostic variables we're using. So that's something that we are looking at now. It just, basically this is increasing difficulty to implement in the model. So like we want to kind of do more tests in LES before we like commit to like really developing like the death of auto-conversion in the global model, but that definitely is an
Hurry
interest
up.
of ours.
Let's continue that research. Anybody else?
Yes, I might have missed this. I mean, how computationally expensive is BOSS versus like the full neural network or the pure physics-based version?
So BOSS is like, in practice, when it's like running in the model, it's basically just like this typical physics approach. It's just a bunch of power laws. I'm not 100% familiar with the neural net speed, but I imagine it's slightly faster just because you don't have to do all these matrix multiplications. Like, I don't know how big those networks are. But it's definitely, you wouldn't expect it to like cost
It
substantially.
definitely doesn't cost more than the pure.
Yeah. So what would cost more is if we started to add a different number of prognostic variables, obviously that would increase the expense. But at the current implementation, it's basically the same prognostic variables, so basically the same cost.
Awesome, thanks.
Alrighty, so let's thank all the speakers from the. Looks like David Mitchell just joined, so he'll probably give his presentation later. So in case I didn't mention it, please eat cake. And there's fruit too. So, we'll reconvene in 10:45.
So all the like, I like the surface met station. So it's like really simple.
Yeah, I don't know as much about it.
I also don't.
This is, okay, that's the missing one.
Oh, no, that's okay.
Dave, can you go full screen?
Stuff like through recording.
You can hear me?
Hello?
Yeah, can you go full screen? Present.
Yeah, I'm trying to, it's all shaded out and I'm not sure what's going on here. How's that?
Yeah.
Okay, good.
I don't know.
Is everybody? Alrighty.
Okay, I can't see anyone unfortunately, but I can see the screen.
Yeah, just, so Dave couldn't make it this morning, but he's here now, but he has commitments really soon, so we're gonna switch the schedule here, so Dave will go first, and then Margaret and Cecile. I don't know if Amit is here, but he's supposed to present. We don't have the presentation, so if you're online or hiding under a chair, please upload your presentation. So that, Mitchell is going to talk about a global seasonal assessment of homogeneous ice nucleation in cirrus clouds and relative estimates of cloud radiative effects. I think that's the longest title we have. Take it away, we can hear you clearly.
Okay, great. So yeah, this is a talk about homogeneous ice nucleation, how we can kind of parse it out. Well, shown in the cover slide here are two types of cirrus clouds that were sort of revealed to us after we got into this work more. We found that the cirrus characterized more by homogeneous ice nucleation was optically thicker or had a larger extinction coefficient, and the Het cirrus didn't. So that's basically the method that we used, but I'll go into the details later. So we developed a new retrieval scheme, Calypso retrieval. And the basic idea is to take field campaigns, and we're interested in certain types of ratios, like N over the area of the size distribution, for example, or ice water content over N or whatever. And we relate those to the absorption optical depth ratio, which is this beta effective here. And another example is the size distribution absorption efficiency, Q absorption here. So all that comes from field campaigns, and they're related to the absorption optical depth ratio, which the Calypso satellite easily retrieves. It's been doing that for decades, and it's been perfected. Tau is the absorption optical depth, and delta Z equivalent is the equivalent cloud thickness that we retrieve with a LiDAR. And the improvement we made was that before we were using N over ice water content, now we're using N over area, which is directly measured by the probes, the air size distribution probes. So that's a direct measurement that improved the retrieval. The effective diameter is retrieved by based on theory, but we can expand that theoretical equation into these two ratios, which are related to the absorption optical depth ratio, beta, and we can retrieve those. So that's how we get effective diameter, and ice water content is obtained from the extinction coefficient, alpha extinction, and effective size, and alpha extinction is given by that formula there. So going on to the key points, we're only sampling single layer clouds that are semi-transparent to the Calliope LiDAR. Most of the clouds have a visible optical depth less than 3. And the Calypso infrared imaging radiometer, it samples cloud layers. It doesn't do in-cloud profiling like the LiDAR could do. So the sampled clouds have a radiative temperature less than 235 Kelvin. And I covered number 5 already. Number 6 is we're using 4 years of Calypso data. So we want to know if the retrieval is making sense or not. So we compared with the cirrus cloud climatology of Martina Kramer et al. And we get reasonable agreement when we use all of the IIR data, the infrared samples, that corresponds to optical depth between 0.005 and 3. And those are the blue curves. And the climatology, the Kramer climatology, really directly samples the number concentration and the ice water content. And then it gets this volume radius by essentially dividing ice water content by N. So the two direct measurements compare pretty well with the Kramer climatology within the 25 percentiles. So the darker shading, gray shading, is the 25 percentile of the Kramer data, and the tropics are indicated by orange and light blue curves. So the darker blue and the red curves are for all, are for all the data. So for ice water content, it also agrees pretty well. So we were happy with that. So we found that when the cirrus clouds are optically thick, but the geometric thickness was thin, we had high number concentrations that could only be explained by homogeneous ice nucleation. And under those conditions, we found that the ice water content was also quite high. And in overland conditions, the effective diameter decreases. It always decreases somewhat under those conditions. So we use the extinction coefficient defined here as a way of separating out those two mechanisms, homogeneous and heterogeneous ice nucleation. And we retrieve these things as well. So when we look at the retrievals in terms of the extinction coefficient and versus temperature, we get these plots here for the ice water content on the left-hand side. And the triangles are, the color inside the triangles are predicted by a model, a very simple model that I'll show in a moment. But the colors in the triangles matching the background that is retrieved from the satellite indicates agreement between the model and the satellite retrieval. So we do this for winter on the top and summer on the bottom, and we are looking at the mid-latitudes and the high latitudes here. And the similar analysis for the number concentration on the right. The simple model we use is indicated there. The colors are more or less similar to what the satellite sees. You can see a gradient in concentration. So the blue colors correspond to heterogeneous ice nucleation, as we'll show later. And the colored, the other colors indicate a gradient. So you're moving from heterogeneous to homogeneous ice nucleation in this gradient here. This is that simple model that we use. It's Clausius-Clapeyron equation, and also the supersaturation equation for homogeneous ice nucleation, giving the threshold for that mechanism to kick in. And that'll give you an equation in ice water content, which is simply the difference of the water vapor density at that homogeneous threshold minus the saturation vapor density for ice. And we also can use that information to, in combination with these d-mean temperature relationships from field campaigns and mass dimension relationships from Irfani and Mitchell paper, and a few other things that give you the number concentration and effective diameter. So effective diameter is shown here, plotted against extinction. And on the right side, we have the probability counts in a way, or the counts total, what the satellite is retrieving and the frequency of retrieval, if you will. And the model is showing the black triangles, like where pure homogeneous ice nucleation is occurring. in these plots. And you can see that the pure homogeneous ice nucleation is just on the fringe of the counts statistics here. So that makes sense because it's a rare event in the atmosphere. It doesn't happen very often. So the way we calculate homogeneous, like if a cirrus cloud is strongly affected by homogeneous ice nucleation, we look at the effective diameter versus extinction, and we find a maximum shown by the vertical dashed line. And if you're on the left side of that dashed line, as a conservative estimate, we're saying that's heterogeneous nucleation, which actually includes some clouds that are affected by homogeneous nucleation. But if you're on the right side of that line, you're strongly affected by homogeneous ice nucleation. The cloud is. So we use that conservative estimate of, and that's shown by the plus marks on the bottom panels here. This is for like tropics, mid-latitudes, and high latitudes. And the horizontal dash line is the temperature at which we no longer see a maximum in the effective diameter. So when you can see like at these blue colors at the bottom of the plots here, it starts fading away. Like you don't get a maximum very well. It's not well defined. That's where you get this horizontal dash line indicating the temperature at which that maximum fades away. So we have this bounded region by plus marks and the horizontal dash line that gives you a region where the homogeneous ice nucleation or the cirrus clouds are strongly affected by homogeneous ice nucleation. And these are the results that we get, and they are zonal means of the home fraction. So that thick black the thick black curve or histogram is below that is the homogeneous ice nucleated cirrus clouds. And the blue colors are for heterogeneous ice nucleation. It's separated into liquid origin and in situ cirrus clouds, but that's a secondary point. The main point is, how it varies with latitude. And if you multiply the fraction of homogeneous cirrus clouds by the optical depth, you get a proxy, a relative proxy for the cloud radiative effect. We determined that by comparing with Hong and Liu's data, 2016 data. So anyway, during winter outside the tropics, this optical depth weighted home fraction shown by the thick black histogram tends to be more than 50%. And that was a big surprise because that indicates that the home affected cirrus clouds contribute substantially to the Earth's radiation budget. And some people were saying it was almost all heterogeneous nucleation. This is a map of the same analysis. It just shows that in this map, we found from the literature that there's more dust in the summertime in the southern hemisphere over the Southern Ocean than the wintertime. And that seems to correspond with less, when you have more dust, you have a lower home fraction in your cirrus clouds versus when you have less dust. So that needs to be developed more or explored more. This is what a 2012 paper by Gettleman et al. Is showing in terms of the comparable home fraction. And it shows like there's less homogeneous nucleation in the northern hemisphere versus the southern, where our results are showing that to some extent, but mostly it's kind of 50-50, as you can see. There was more of a equal partitioning, not in the DJF, and it was a little more like that Gettleman paper is showing, but in the summertime it was different. So, and here's a global map of that as well. So anyway, in summary, we found we developed a new retrieval, Calypso retrieval, and we found agreement between theory, home theory, and Calypso retrievals that where it's corresponding to a region of pure homogeneous nucleation. Number 3, the retrievals of the shortwave extinction, effective size, and temperature were used to estimate the fraction of cirrus clouds that were strongly affected by home. And over the oceans outside the tropics, the zonal mean fraction for the home affected cirrus generally ranges between 20 and 35%, with comparable contributions from in situ and liquid origin cirrus clouds. And number 5, the optical depth weighted fraction of the home cirrus was used as a relative proxy for the cloud radiative effect. And over the oceans outside the tropics during wintertime, this tau weighted fraction was more than 50%, showing that the home cirrus are radiatively important. And the last point is that the home fraction appears anti-correlated with inferred mineral dust concentration from the literature. And we need more research to substantiate that. So thank you. That ends the talk. So
Something went wrong. Please try again.
John? I didn't completely get whether you think that the model parameterizations need to be evolved, let's say, to better reflect what you're finding. And as a separate question, do you think this potentially has is there an obvious implication on climate sensitivity for this?
it could be. I think the first question, we're working right now with CAM6, trying to find a way to parameterize these results in the model, and still working on it. We've been in contact with Andrew Gettleman on that, and he's been very helpful. But yeah, for a real robust model parameterization, one thing is the pre-existing ice assumption. It tends to quench homogeneous ice nucleation, and it seems like it's pretty effective at wiping out the contribution. So some recent papers, one by Decoitzidis et al., is showing that this homogeneous nucleation is occurring near cloud top mostly. And if you're looking at like a 700-meter layer in your model, and you're using the layer average ice mixing ratio and that goes into the pre-existing ice equation. It's really the supersaturation development equation. Then you're going to overestimate the pre-existing ice effect. So if you were to use just the ice mixing ratio near cloud top, it would be much smaller than that, and that would give you a better result, I think.
All right, thank you.
So what was the other question?
Just whether there was any implication for effective climate sensitivity, if there's anything obvious in your head about what this might mean.
Well, it does make a big difference in your microphysics of the cirrus clouds. So I think that's a possibility, but I don't know the answer yet.
Righty, thanks, Dave.
Yep, thank you.
Sorry to unlock the laptop here, but once that's done, it's time for Margaret Duffy talking about CAM6 SST patch experiments. Do you want to use the electronic pointer? You just have to your little patience. All right, thank you. Take it away. There you go.
Yeah, okay. Okay, that's fine. Okay, so hi. Margaret Duffy. I'm going to talk about some CAM6 patch experiments. Really, the main purpose of this talk is just to serve as a public service announcement that these experiments exist, and you can use them if you're interested. So if you want patch experiments, please don't go out and rerun them because we already have them. I could sit down now, that would be, that would be most of the talk, but, okay, what are patch experiments? Why did I spend time running these and why might you want to use them? In this case, it's an ensemble of atmosphere-only experiments with, atmosphere-only experiments have imposed SSTs for the lower boundary condition. And in this case, the ensemble has, the SSTs have little patch-shaped anomalies in different locations across the ensemble. And these experiments are useful for diagnosing the response of the atmosphere to local changes in SST, and people use what's called a Green's function approach to reconstruct whatever feature of the atmosphere they're interested in from these patch experiments. Okay, so this is most commonly done to study what's called the pattern effect, which many of you probably know what this is, but I will remind you. So what this map is here on the slide is a map of the global mean radiative feedback for a change in SST at that location. So it's not a map of it takes a second to get your head around this. It's not a map of the radiative feedback, but rather a map of where SST is having the greatest influence on the global feedback. So we can see that if we warm the tropical West Pacific Indian Ocean region, that has a very stabilizing impact, stabilizing influence on the radiative feedback, whereas if we warm the East Pacific, that tends to increase the feedback. Okay, this radiative feedback has a lot of implications for the climate sensitivity. As a corollary to all of this, the pattern of SST warming has a big influence on the climate sensitivity. And as the SST pattern evolves over, say, long 4 times CO2 experiments, the climate sensitivity, the feedback can change over time, and that's sometimes people call that the pattern effect. It's not a super well-defined term. People have also used these Green's function type simulations, these patch experiments, plus a Green's function approach to recreate the response of precipitation to warming. So this is, again, the global mean precipitation response as a function of local SST change. So we can see, again, this outsized influence of the tropical West Pacific region. The confounding, it's probably not a coincidence that the precip and the feedbacks have similar maps. The confounding variable there is clouds. So that's another example of things that have been done with these patch experiments. The ones that I just ran more or less follow the GF-MIP protocol. So there's a Green's function model under comparison project happening, and we're making a contribution with CAM6. This is a table from the GF-MIP protocol paper that just came out, and I've highlighted where ours are a little bit different from what GF-MIP did. And the reason why there are differences at all is that I wanted to have the same setup as the CAM6 PPE so that we had like apples to apples comparison between the influence of SST uncertainty and parametric uncertainty on the atmosphere. So this is all the same tag and ComSet as the CAM6 PPE, which we've been hearing people talk about. So the patch experiments are 8 years long, and the amplitude of the patches are 2K warming. We also have some shorter ones with negative 2K cooling. And they're run with the F2000 ComSet. This is the CAM tag that we used, and we did that to match the CAM6 PPE. Let's see. This is a map of where the patches are located. So each one of these patches is basically a different ensemble member where the SST is warm or cooled at that location. A little science, hopefully at the next one of these I'll have more science, but just to get started on what I'm doing with these, much of the influence, much of this map that we saw at the beginning, this radiative feedback, which is so sensitive to SSTs. A lot of this is operating via cloud feedbacks. So this is from the CAM4 patch experiments. We can see that in particular, the shortwave cloud feedback is a very dominant contributor to global cloud feedback in terms of the sensitivity to SST pattern of warming, with some compensation by the long wave cloud feedback. So this is our total feedback on the left, short wave cloud feedback in the middle, long wave cloud feedback on the right. These have also been run in CAM5. So here are our two cloud feedbacks that we just saw for CAM4 from Yue Dong. Chen Zhao did this in CAM5, and now I've done this in CAM6. You'll have to forgive this slide. It breaks all the rules for different map projections, different color bars, different. So you have to splint at this and not take this too seriously. But the big picture that this kind of outsized influence of the tropical West Pacific that holds up across the 3 different generations of CAM that this has been studied in. One thing that is unique about the CAM6 patch experiments, as compared to previous versions, is that they were run with the COSP simulator turned on. So we have all of these additional outputs related to basically clouds. And so this was our cloud feedback that we saw in the previous slide in CAM6, and now we can decompose it into contributions from various individual components of the cloud feedback. So we can see the tropical, this is the tropical low cloud feedback is playing a really big role in the total cloud feedback. We can learn that from the CAM6 patch experiments because of having the COSP simulator turned on. One big caveat, and something that I'm spending a lot of my time concerning myself with, is that the Green's function, so you have your different patches, and the Green's function approach basically takes a weighted sum over the patches. And if you wanted to reconstruct, and then you reconstruct, say, in this case, a uniform 2K warming experiment in blue, but that there's actually some nonlinearities in the system, and so these don't inherently add up. That's not terribly surprising, but I think it adds a caveat to how to interpret the maps that I'm showing you. This is where they're located, but in practice, if you want them, you should just email me. Not try to memorize this. Okay, yeah, so summary. So if you take one thing from this talk, it's that CAM6 patch experiments exist, and so if you want to use them, you can. And preliminary results show that the cloud sensitivity to SST is similar across CAM4, 5, and 6, at least qualitatively. And I've been spending a lot of time worrying about this non-additivity. So if you have any thoughts on that, I'd be happy to hear them. And yeah, thank you for paying attention, and my email's on the slide.
Questions for Margaret? Julio?
Thanks, that's interesting. Could you just interpret the first plot you showed a little more? I'm sorry to be slow.
Yeah,
but...
no. I spent a lot of time sitting here staring at this figure before I understood it. So this is a map of the sensitivity to the global radiative feedback, so the feedback parameter lambda, which is one number per patch experiment. And then the map is showing where the SST was perturbed in that experiment. So this is the sensitivity to the global feedback to SST perturbation, SST warming at that location. So if we warm the tropical West Pacific, this big blue blob here, that has a stabilizing influence on the feedback parameter, and where it's red, that has a destabilizing or an amplifying influence on the feedback parameter. I know, it's not what we're used to seeing, so it takes a second. But this is sort of the, canonical picture of the pattern effect that we think of, yeah.
Have you looked at the comparison to parameter perturbations?
Yes. so far I'm just really confused, so I didn't, so far it's just been really confusing, and a lot of data, and it's been hard to disentangle what to make. But that was the intention behind running these and running them in an apples to apples way, was the big picture was to try to get a sense of the relative influences of the pattern effect versus parametric uncertainty on cloud feedbacks. It's work in progress.
So then would you look at the PPE or sort of the subset of PPE members that fit certain metrics?
I have been looking at pretty much the whole PPE. I've whittled it down to those, some subset which are somewhat more realistic, so from 260 to about 200. And I think, maybe that's a good way forward to try to reduce some of the confusion. Having the kind of Latin hypercube setup adds to kind of the difficulty of comparing, adds to some of the difficulty in interpreting parametric sensitivity.
John?
Just building on Julio's question a little, this plot, you've explained what it sort of says. What does it tell you? What do you understand from looking at it?
So what we understand from looking at this is that radiative feedbacks are very sensitive to the pattern of warming, right? And in particular, the gradient of warming over the tropical Pacific is really important. So a lot of times, we'll run a 4 times CO2 experiment, and over time in that experiment, this gradient will evolve, and that will change the feedback over time. And so that might be, for example, so we might expect from that the climate sensitivity to increase with time as the SST gradient responds to the CO2 forcing.
You think this is dominated, this looks like it might be dominated by clouds, right?
Clouds and also lapse rate is another important feedback that's
High clouds?
actually low clouds. So a lot of what happens here. So the mechanism, the hypothesized mechanism for what's going on here is that you warm the tropical West Pacific. The tropical West Pacific is a convectively active region, and it communicates very effectively with the free troposphere. So when you put warming here, then that has, through the what's called weak temperature gradient approximation, the warming in this region has an effect on the whole tropics. That then can have this kind of remote influence on the low clouds in the tropical subsidence region, which are very bright, reflective, high albedo, and stabilizing. And so if you reduce those clouds, that has an amplifying effect. If you increase those clouds, it has a stabilizing effect. So that's the kind of picture of the mechanism that the community has put forward. But I think there's still some debate as to exactly, how oversimplistic, to what extent that's oversimplistic or not.
Just to add that the observed pattern effect is that the East Pacific hasn't warmed as much as we expected it to, but models think it does. And this might help to explain why models and observations disagree in the last 30 years.
Right, so this is kind of telling us, so we know that the modeled and the observed SSTs aren't always agreeing with each other, especially in this region. And this figure is telling us why that has an impact on the global climate.
Righty, thank you, Margaret.
Thank you all.
Next up is Cecile, who by mistake I only gave her 10 minutes, but you can have as long as you want. Apologies for that.
I'm going to speak very fast.
Right, so Cecile is going to talk about exploring a simplified slab ocean model, which is different than the title here.
Yeah, it's because this one was too short. Yeah, then we have been exploring a simplified slab ocean model, and we have been using the equilibrium climate sensitivity to assess the validity of this simplified model. And it's something that I have been doing mainly with Julio, but also with contribution of Jiang, Dave, and Brian. Then basically this is the slab ocean model, then it's a mixed layer ocean model with prescribed ocean heat flux, what we call the Q flux. And the issue with the slab ocean model is exactly this Q flux, because the estimate of the Q flux is quite resource intensive. We compute a Q flux, we need first a well-balanced coupled simulation, and also this Q flux need to be computed in the same configuration as the coupled model that we use. Then it's kind of expensive. Then what we wanted to do, our motivation here, was to develop a simpler and cheaper sum configuration that preserves some key aspect of the coupled system behavior. And also we are going to evaluate this, the ability, the performance of this new sum configuration by looking how it represents the climate sensitivity. Then basically, this is the way that we estimate. There are several methods, but one of the methods that we have been estimating the climate sensitivity in CAM is to do a run with the slab ocean model. And why do we do this? It's because it equilibrates very fast in a few decades instead of 1,000 of years for the coupled model. Then basically, this is what we do. We do 2 60-year simulation. Here there are a little bit more, but we do 2 60-year simulation, one with 1 times CO2, one with 2 times CO2 in the coupled configuration. And then we look at the year 40 to 60, and this is when it's more or less equilibrated. Sorry, do you have the other thing? This is where it's the top one. Then it's more or less equilibrated, and this is how we compute the sensitivity. Then the question that we had, and I have shown this before, it was how much of the detail of the Q flux will matter. Each time we recompute a new Q flux for a new model configuration, but here I'm looking at the Q flux in CSM1 and CSM2, and basically they look fairly similar. Then we really need to do this. And then also we wanted also to go further, and it was to use an idealized Q flux to assess the sensitivity. Then first we decide, okay, we are going to swap these two versions of the Q flux, and the first plot I had already showed this. When we did this, when we substitute the Q flux from CSM2 by the Q flux from CSM1, we saw a catastrophic cooling that originates really in the region here in the Southern Ocean, around here, and then it propagates very quickly to the other region. And it's due to the sea ice that start to grow, and then we have a runaway simulation very fast. Then we try several things to get rid of this, and then at some point, with discussion with Dave Bailey and Julio, we decide we want to use a model without the sea ice. We are going to remove the sea ice. Dave was originally a little bit reluctant to do this, but he gave us the code how to do it. And then when we do this, this is when we are going to call the sum no ice. You see that it's stabilized. The previous one, it's the red without and the green without the dot, and you see that you have this cooling. Then it's going to equilibrate at a temperature a little bit warmer than before, but you see that now we prevent this cooling that we see before. Then we can use the CSM1 or the CSM2 cooling. Then can we use this sum no ice to estimate the climate sensitivity, and I'm going to call this the ECS no ice. And basically this is what we found. Then you see that now you obtain a climate sensitivity without the model that's about 1.2 degrees lower than the climate sensitivity with the full sum. And basically it's because we have the sea ice feedback that's missing in this sum no ice. And we decide, is it even useful to have this quantity? And then we start to look at the relationship between the climate sensitivity and the climate sensitivity noise, ECS and ECS noise, and we test this on a set of parameters, the heterogeneous freezing off that Jiang studied. Then we also test two parameters that was coming from Brian and Margaret, DCS and C8, and we also turn CAM6 to CAM5. And when we do this, then you see that you have really a strong relationship between the ECS and the ECS noise. And it's a decent indicator of ECS change during model development. And you're going to say, does it offer more compared to SST plus 4K? And indeed, we obtain very similar result. It's the method, of course, we do something more expensive than the SST plus 4K because we run much more here. But it has the potential here now to investigate some aspect of the ocean heat flux when we use the sum noise. Then we went even one step further and we decided to try to use idealized Q flux. And we did we did many versions of the idealized Q flux, but I'm going to show here two versions that we did. The first version, we just did a zonal Q flux. On the top, I'm going to stop to touch this. My slide jumping around. On the top, we use zonal Q flux, and on the bottom, we use piecewise Q flux. Very simple one. And then when we do this, you look here at the ECS noise that we obtain in these two configurations, and you see that with the idealized Q flux, with the step one, we obtain climate sensitivity that's really similar to ECS noise, very similar to the one that we obtain with the global Q flux. Of course, it doesn't tell the whole story because it's a single number that's not going to reflect regional change. And here I'm looking at regional change between the ECS noise for the piecewise Q flux and the global Q flux. Okay, then this is a summary. Did I do my 10 minutes? Then our goal was to explore a simplified slab ocean model, and we developed this sum noise with idealized Q flux, and we assessed the performance on the equilibrium climate sensitivity. And we see that the sum noise allows us to predict the change of ECS during development, the change to physics and parameter. And we saw that using idealized Q flux produce ECS noise that's similar to the full global Q flux. The caveat is that it's a single number that doesn't reflect regional difference, but it has the potential to learn more about the couple model. And the next step, we want to examine the regional difference between the idealized and the full Q flux. Okay, then this is what I wanted to show.
Questions for Cecilia? I think Isla was first.
When you say noise, is it really noise or is prescribed to some value?
We remove, there is absolutely no noise. We remove all the CIs.
Margaret?
Yeah, I'm curious what model tag you're using for CAM6, because Brian and I also found like a pretty big sensitivity to the specific version of.
I use CSM2.
Yeah, and then, but within that, like 6.0 to CAM 6.0 to CAM 6.3 had a pretty different climate sensitivity, so I just wanted to.
Yeah, but this is, I'm using the CSM2, I'm not using any development version. All the simulation are here done with the CSM2 that had the large sensitivity of 5.3.
Yeah, that makes sense.
Yeah.
That's what I would have done too, yeah.
Adam?
I thought the scatter plots of the ECS were interesting, but I didn't quite digest them. I was wondering if we could look at them really quickly again. Yeah, this one. So on the right, the ECS noise is on the x-axis, but what's on the y-axis?
Here,
Yeah, for the slab ocean one, yeah.
oh, yeah, then this is the ECS that we did with the ECS no ice. We did the simulation with the ECS no ice and with the sum no ice, but also with the full sum to see if we were obtaining the same result.
So, okay, so the y-axis is with ice on.
Yeah.
So that's the real ECS, right?
Yeah, it's the real ECS.
It's the real ECS using,
It's the
Using a slab ocean.
using the full sum model. It's the real ECS using the full sum model.
oh, okay, so it's not using like the wrong Q flux and causing excessive ice buildup. That's not the solution you're showing on the y-axis. You're showing the actual ECS estimated using the correct Q flux.
Yeah.
And then I was just curious about this, the plus 4K SSTs method. Does that provide like systemically lower ECSs compared to the slab ocean? I thought that this would be,
Yeah, here I'm computing this lambda parameter. It's not really the ECS. I'm looking here just the relationship between the ECS. Sorry, I'm pointing to my screen and you can see
Okay.
what I'm pointing. I'm just showing the relationship between the lambda and then the change in TS divided by the change in restom compared to what I will obtain in ECS. Then basically the y-axis here, sorry, I might have confused people. The y-axis are showing the result I obtained with the full sum, the two y-axis.
Gotcha.
And the other one show what I obtained with the SST plus 4K and the EC and the sum no ice.
so I interpret that both of these methods will at least tell you whether one version has a different ECS than the other. They both look to be
Yeah.
fairly useful.
Yeah, and I was, it really helped during model development just to see if we want to know the change of a parameter, we can look really quickly at this.
Okay, thank you.
I'm just wondering, could you comment on how concerning it is that small perturbations to the ocean fluxes can plunge us into snowball? You were showing those plots, they look very similar.
Yeah, then this is, the sum is built in a way that it's going to use the Q flux that's coming with from its own version. And it's not you can use sometimes Q flux from another version and it will still work. But it's really small instability that are happening that create this behavior. And it will not, and I don't know a lot of use of the sum, except usually to look at the climate sensitivity. I don't use the sum for anything else, but we were thinking we would like maybe to use it for something else and see what are the limitations of this model. And Zhang think that we could change the way that we compute. Do you remember what he had said then?
It was the time stepping in the sea ice. He was suggesting that the SOM is working with a simple forward time step, and that if we do something more sophisticated with the SOM, then maybe this won't happen, but we haven't checked that.
I guess I'm a little confused. It's been a while since I've thought about this, but how is the CS behaving on top of the single level ocean in terms of forming new sea ice? Is it doing it exactly the same as the couple model would do?
Yeah, you don't prescribe the sea ice, you prescribe the initial condition of the sea ice, and then the sea ice can melt or grow. And then it's really what's happening in
Can
the.
it move? I mean, is it melting in situ? Is it moving, you know, dynamics of the sea ice versus, a column forms that is now, because of the SST is below 1. I'm just a little confused of how, is it that, I don't think it's the whole piece of the coupled sea ice model that is happening here. I feel like it's these individual columns that start to form and then grow, which of course, if you think about it, that causes problems because you're using the same, you're still applying, I believe, the same Q fluxes, even though ice has started to form. So that's a little odd, you know, because you're taking it from the couple model where there's no ice and, you know, the surface fluxes are what they are. But I think still applying that when the ice is growing, where in the couple model there was ocean, that I think there's a little something odd going on because of that. I don't know what in terms of, but I feel like you maybe should do something different if ice starts to form, turn off those Q fluxes or something, I don't know. Sorry, that wasn't the question, that was just, babbling.
Well, I think that's exactly why we decided to try this no ice
Yeah,
configuration,
absolutely,
because there is this problem, the Q fluxes are calculated with a certain sea ice, and then suddenly there's
really
no
inconsistent,
sea ice
yeah.
above you, or there is suddenly sea ice above you, and the
I'm
Q
just
fluxes
wondering whether you
don't.
can modulate that.
The plan was to fix this with there, but then at some point we didn't have a way to fix this, and it's why we started to try just to remove the sea ice to see what happened, and then we found it was interesting to explore this configuration.
As a warning to the other components, we'll take you out if you.
Got lights, we're coming to you next. No atmosphere.
I'm just wondering if prescribing ice is an option, if that would be a smaller to have prescribed ice and no change versus having no ice at all would be a smaller.
Yeah, and we wanted exactly to do this, but then there was not an easy way to change it in the sum.
And if you have a strongly warming, I mean, the 2 times CO2 can get really warm, and you'd be stuck with this situation where you've prescribed the sea ice in a warm climate where it should melt.
But we also are in a situation of having no sea ice in a climate that's.
Yeah, that's like that better.
I mean, originally, the original CAM SOM was like that. My recollection was it was more like AMID. You prescribed the sea ice, but this is the CSM SOM, which is different.
Yeah.
So I'm wondering, but that was a good point.
Yeah, if there's a technical problem with prescribing sea ice, there is a way to calculate the thermodynamic effect of sea ice as a Q flux very easily using fully coupled data. So that's one, I can show you how to do that easily in the form of a Q flux so that you still get the right climatology of temperature and as if there were sea ice there.
Yeah, it's good.
John? I guess it's thinking about all these options, it's kind of worth thinking where you're trying to get to. You've sort of shown that you get rid of the ice and you can see this correlation that you were sort of after, and it's one option. So I haven't quite got in my head where this goes and where because it looks a lot like you said the 4 times experiment is quicker.
Yeah.
So you're introducing a certain level of complexity to learn something more.
Mm-hmm.
What do you need in that something more, and what is that something more you're going to get?
Yeah, this is, we don't know. We have think a lot to try to find a justification to what more we can find, and we don't know yet. We think we can. There is more that you can get because you are keeping some aspect of the couple model. It's still a couple model, even if it's just single layer ocean. But
So you think about that and then you work out which one of these three
Yeah,
methodologies is the right
which
one to choose,
yeah.
basically.
Yeah. Yeah.
All right.
The overall problem is we need fast diagnostics of this quantity during model development. If it's been a year, I mean, it's been a couple weeks, I mean, we probably have gone a year or two without testing ECS.
Last time we tested ECS, it was in 26J.
Yes, that's a while ago.
Yeah.
Right,
I'm doing it right now.
Oh, we're doing it right now, yeah.
But not, right now I'm doing a 4x CO2 coupled, and it's different. We test with the ECS in 26J, but there were a lot of issues because also all the script that we had were for POP, and now we move to MOM, and computing the Q flux, if we need also to rewrite script to compute the Q flux.
Yeah, I don't totally know where, this might just be a comment, but I think it's really interesting that the 4K ECS, 4K warming, ECS, and the SOM ECS were very similar across the different perturbation experiments that you did. I think
It's reassuring that both methods give the same.
it is, but there's a pretty big difference between ECS in atmosphere only and in coupled runs. And so SOM could be a nice way to dissect why there's such a big difference between, the atmosphere only and the fully coupled. But it's, I just thought this was interesting that 4K and SOM have similar ECS values.
Is it reassuring or is it disappointing?
I was, to tell the truth, I was really disappointed.
If you were saying you were doing more complexity to
Because
try and understand some
yeah.
difference, and they both look the same, then it seems like you haven't captured.
Yeah, no, I was a little bit disappointed. I saw it would not perform as well, the SST plus 4K, but it works quite well to predict direction of the change.
But not linked to the couple.
Yeah.
You haven't gained, it's like you haven't gained anything.
Yeah,
If it looks exactly like that, you've not gained anything. If you
If
see
all
differences and it corresponds.
Yeah, if all you're interested in is predicting ECS, then there's still, 4 plus 4K is probably quicker.
Yeah.
People are quite often asking for a slab ocean model for other reasons too.
Yeah.
So it seems like useful to be able to just.
Yeah, and it was, and because we didn't want, we did like many things, and I'm just selected some no eyes here to show, but our idea was to do a simplified sum, and we wanted really, this is where, at the beginning it was really what we wanted to do, a simplified version of the Q flux in a slab ocean model. But then we were having all this issue of instability, and then it's why we started, at some point we wanted to see what was going to happen without the CIs. But, it was to build a simplified sum, but not necessarily the sum no eyes, but it was a simplified sum that doesn't require all this gymnastic every time when you want to have a new version of the model, and then you have to do a couple simulation, recompute the Q flux, and it's what we wanted to avoid. But I agreed. Originally, the idea was to do a simplified sum.
Have you tried a 2 degree? Because the easy thing to see if you 2 degree model as opposed to 1 degree.
No,
Just take a 2 degree and apply the 1 degree flux. I'm just wondering whether that's an easy multiply by 4 efficiency.
Yeah, I was asking Marcus, like, we had a PP at 1 degree, we're interested to do it at 2 degree and see if we get the same parameter dependency. It would be 8 times cheaper. Right, thank you, Cecile. That was way more than 10 minutes.
So greedy.
So the next 2 presentations have been cancelled, so we're going to break for lunch and be back at 12:45.
What time do we come back?
12:45, in an hour.
example, I think the way I caught it was riding on the light rail from the airport to downtown. The train was full.
Assume that you're not going to these 2 p.m. CCPP.
Really, just full, and they were all talking to me.
I might try to go if it ends.
Well, hopefully, well, it sounds like. After 2.5 days, I
Confused
actually.
with the email we got from Woodline.
I did Paxlovid.
Oh, yeah.
But then my wife got it a few days later. And so she went on Paxlovid, she's better.
And then talk about.
Yes, I'm glad I took an Uber from the airport.
Yeah, but that day, taking a taxi from the airport to downtown was problematic.
Yeah, I didn't get in until, took a later flight, we got in at,
Game was over.
no, right, we got in right like after it started. I drove by the stadium
I see,
when it
well,
was
traffic was
full.
better then.
And there was like, that was the best time to go, like an Uber was cheap and there was absolutely no traffic and we drove right by the stadium because.
Yeah, I was trying to come to
Right.
He's not gonna be at the
He's got that key flux, otherwise it will drift to a very unpredictable state. There's no way for it to dissipate from the tropics to the extra.
It's more important.
Yeah, but it's sort of like the ending of flux allows it to.
Hey, man.
Which came from NT, so
Since your previous network's like IFS, do you have options to do like
it's not necessary, but if
the activation actually within
it's.
Yeah, you can turn on, well, you could just turn on Myers, that's what it is.
I mean, it can only.
Okay, so that way it's just, there's very little going on and sort of and drop.
It's always going to be exporting within.
For the ice, it still works for liquid.
So the Q flux small.
It does still work for it.
Yeah, you can set the number of concentrations to be constant, which mostly shuts it down.
So it can.
Okay, I got
There
you.
is some variability, it definitely locks, it removes kind of any variable effect.
Sort of like a slower.
So it may not, the biggest problem with fixing the number concentration is globally it's not a great simulation because you kind of need, it's designed to have different number concentrations and it's just a global number.
I got you.
So it
But the
works
first
great if
two,
you want to
they're
tune
gonna
it
share
for a
their own.
scam case, but it
Oh, wow.
doesn't.
So how does the warm rain microphysics, warm rain
They're not
microphysics
able
do?
to.
Well, it just takes the number.
So the number's still predicted by the header,
So the number's predicted by end drop.
yeah.
And you can shunt that off and put in a fixed number, which is then used throughout the microphysics.
In
Yeah,
your,
okay.
in your time
Yeah,
series.
so wondering.
But the ice nucleation is set to use, you can flip a switch and
It goes up.
It can use the internal
It
Myers.
uses the internal Myers and ignores everything. So yeah, if you wanted to remove that sensitivity, that's easy.
And then it levels.
I talked to, if you're gonna use a fixed number, you can talk to me, just.
I'm just curious more about the width or why or something inside, so now I'm getting some sort of.
The reason why it's outside is because the microphysics, we didn't want the microphysics to do the aerosols because we wanted to just tell us what the activated number is.
There's several markets.
Yeah, exactly.
I know, I feel like we're not gonna get it.
But cleaning up.
So I'm Sean Santos. I've been deputized by Hui Wan, who unfortunately did not make it today, to help chair the meeting. So you've got me to host for these last few hours of the meeting this year. So the first talk that we have is by Cara Lam at Columbia University. And looks like Cara is here. You ready to share screen?
Yeah, can I share directly?
Should work, yeah.
Okay. Check. Okay, does that work?
Yeah.
Okay, you're seeing the right view. Okay, just making sure. So hello, everyone.
My name is Kara Lamb. I'm a research scientist at Columbia University, and I'm going to talk today about some work that we've started doing and we're planning to do over the next couple of years through the LEAP Center at Columbia on developing a machine learning enhanced unified ice microphysics scheme for CAM6. I just want to start by acknowledging my collaborators on this work, Joseph Coe, Trude Eidheimer, Hugh Morrison, Jerry Harrington, and Marcus Van Leer-Walke. And I'll start with the motivation for this work, which is some of the current issues that we have with existing cloud microphysics schemes. And we can largely talk about two broad areas. One is that we don't fully know all of the physics. In particular, for ice microphysics, a lot of the processes, such as vapor deposition, aggregation, or secondary ice production, or ice nucleation, are uncertain from a physical perspective when we don't have a good grasp on a physical basis for all of these different processes. And then the other challenge is we don't know the optimal way to represent these processes in models. So here I'm just showing a typical bulk scheme that classifies the cloud particles into a number of different categories. And while this is the basis for many schemes, there are some challenges with using these types of ad hoc separations between different cloud particles. So in particular, the current MG2 scheme, microphysics scheme, which is in CAM6, is this scheme which includes two different hydrometer classes for ice, which is what I'm going to focus on in this talk. So there's cloud ice, which is non-precipitating ice, and then snow, which is precipitating ice. And then each of these ice categories is assumed to have a fixed mass dimensional relationship. So we can represent the mass dimension as in terms of these parameters, alpha and beta. So this presents a number of problems. Of course, real ice particles have much more complex shapes than can be described by this very simplistic mass dimensional relationship. I'm just showing some examples of real CPI images of ice crystals. And having these two separate categories for ice and snow leads to discrete abrupt changes in this mass dimensional relationship in converting between ice categories. And this ice-snow auto-conversion parameter, which describes this threshold between the cloud ice and the snow, is something which is unphysical. And also alpha and beta are uncertain and unphysical over large parameter ranges. And we know that having a constant mass dimensional parameters cannot realistically capture particle growth histories. And CAM6 currently demonstrates significant sensitivity to ice microphysics, and this it is in part related to the sort of parametric and structural uncertainty in terms of the representation of ice microphysical processes. So as I mentioned, there's this ice to snow auto conversion threshold because we have these separate ice categories, which is unphysical, and it's also poorly constrained by observations. And in this recent perturbed parameter ensemble of CAM6 that was submitted by Duffy et al., they found that one of the three parameters with the greatest influence on cloud feedback in CAM6 is this ice to snow auto conversion threshold. So this suggests that there's a need for both an improved observational basis for the ice microphysics schemes, as well as rather than just improved tuning of this one parameter. And in addition, in MG2, the particle mass, projected area, and terminal fall speeds are currently not treated in a consistent manner, which means that there's inconsistencies between things like fall speeds and the radiative effects of ice crystals. And we know that there's significant sensitivity to ice fall speeds in terms of cloud forcings as well. So there's been a number of there's been recent work on developing what are these sort of unified ice microphysics or unified microphysics schemes that instead of having separate categories for different cloud particles, instead predict particle properties. And so, for example, there's this P3 scheme that was developed by Morrison and Milbrandt in 2015. And in this scheme, instead of having the separate ice categories, they allow this mass dimension and area diameter relationship to evolve smoothly, which removes this unphysical separation between ice categories. So you no longer have these abrupt changes due to these auto conversion processes. So there was a recent study in 2017 by Trude where they modified MG2 to be a unified ice microphysics scheme and then implemented this in CAM5. So the microphysical parameters were formulated in terms of these self-consistent mass dimension and area diameter relationships that vary with particle size. And they looked at calculating those in two different ways, one based on cirrus observations using a second order polynomial fit to some observations from the Spartacus field campaign, and another approach based on this P3 method. And so here I'm just showing a figure on the right from that study. It's showing the difference in shortwave cloud forcing and long-wave cloud forcing between the cirrus observation-based scheme on the left and then the P3-based scheme on the right relative to the typical MG2. And I think the main takeaway from this is that there are whichever of these two methods you use to derive the self-consistent MD and AD relationships, you find significant differences in the shortwave and long-wave cloud forcings in the tropics in particular. So the motivation for our work is to build on this work and develop an updated unified ice microphysics scheme. And we are doing work through LEAP at Columbia to also bring methods from machine learning into improving our parameterization of different processes. So we're going to focus we like to focus on two particular improvements to this unified ice microphysics scheme. One is an improved physical basis for some of the ice microphysical process rates based on a reexamination of in situ observations using some methods from machine learning. And then the other is improving the observational basis for the mass dimension and area size relationships by significantly expanding the observational basis to include data from 12 past aircraft campaigns. So I'll talk first about improving the physical basis for ice microphysical process rates. So this, and I'm looking first at vapor deposition. So this is some work that I've been doing recently, which is looking particularly at the diffusional growth of ice from the vapor phase. So this is basically when we have ice crystals growing in the atmosphere, they're going to grow through directly having water molecules from the vapor phase attached to the growing ice crystal. So we can write down these single crystal ice growth rate equation. And we know this fairly well, although there are some parameters such as the deposition coefficient, which describes how efficiently water molecules attach to the growing ice crystal, that are still very uncertain, and we don't fully understand these parameters, their functional dependence. And this deposition coefficient also just can be used to parameterize the shape of ice crystals, because you can have different deposition coefficients on different faces of the ice crystal. So as far as data sets, I'm looking at data from the AIDA cloud chamber, and these are data sets from 48 adiabatic expansion experiments. So the typical approach that we would use to evaluate ice growth models against cloud chamber experiments would require some assumptions about the underlying ice growth model, and then we would typically fit parameters to find the optimal parameter choice for comparing against the experiments. So what I'm trying to do instead is to use machine learning to learn unknown physics without some a priori assumption about the ice growth model. So the first thing that you could think to do is just to try to predict the ice water content inside the chamber during a cloud chamber or during a cirrus formation experiment using the observed pressure, temperature, ice number, concentration, and saturation with respect to ice. And here I'm just showing training on a number of experiments. This is showing the predictions from a neural network, and then the true observations in black. And then you could test that against a different set of experiments. However, because this is just, this neural network is effectively a black box, this doesn't actually give us any new information about the physics. It just tells us that we're able to do this type of mapping. So instead, I'm going to look at methods where we can add a lot of physics to the machine learning model, and this allows us to improve interpretability, and it also means that we don't need that much data to get improved generalization performance. So one of the main issues with the in situ observations is that we're trying to put constraints on the single particle mass growth rate, but our observations only provide constraints on the integrated ice water mass per volume in the entire cloud. And so I'm going to develop a hybrid physics machine learning model where I can try to directly learn the functional dependence of the single crystal ice growth equation. So I start with that single crystal ice growth equation, but I'm going to replace this deposition coefficient parameter that I don't know with a neural network. And so that neural network is effectively a function that takes in the saturation, observed saturation and temperature, and then given the weights of the neural network, it's going to predict this parameter. And we also need to, this is the growth rate equation, so we actually need the mass because we observe the integrated ice mass. So in order to integrate over this equation, I'm going to use this approach called neural ordinary differential equations. This was introduced back in 2019. This is basically a way where we can perform efficient backpropagation through ODE solvers using this adjoint sensitivity method. So basically we're able to integrate over a hidden state, a neural network, or in this case, it's this equation, including this neural network, which is parametrizing alpha. And then within AIDA, we also have a spectrum of ice crystals of different sizes. So we actually need to sum over a number of different ice bins in order to do this prediction with this neural network, which is parametrizing the alpha parameter. And this is all implemented in PyTorch. And then I'm going to basically sum over all of the ice bins growing simultaneously to predict the total ice water content, which is what we can actually constrain with the observations. And using this method, you can directly then do backpropagation through all of the ice bins to optimize the neural network weights for that deposition parameter simultaneously. So here I'm showing an example of the node model optimized against the cloud chamber observations. So here, this is the total ice water mass in one of the experiments as a function of time. And then the red here is showing the true observations, and then the black is the prediction from the node model. And because the model is optimized against the observations, that had to effectively learn the optimal functional dependence for alpha as a function of saturation and temperature. So once I've optimized the model against the observations, I can then look at what the neural network had to learn as a function of saturation and temperature. So this is what I'm showing here, this alpha as a function of saturation that was learned directly from these observations. So I'm now working on expanding this was looking at a single data set. So now I'm expanding this to all of the data sets to try to put improved, to give us an updated understanding of the functional dependence of alpha across this range of different experiments that we have. So the other work that we're starting to do is to think about improving the this unified ice representation with in situ observations from 12 past aircraft campaigns. So this is based on using a data set of CPI images that was, this was from 12 past NASA and DOE aircraft campaigns that was compiled by Kara Solia's group at the University of Albany. And the idea here is to use methods from computer vision applied to these CPI images to derive improved and self-consistent mass dimension and area size relationships derived directly from the observations. And this is going to give us a significantly improved observational basis for this unified ice microphysics scheme that we're developing. And we're also thinking about exploring other alternative approaches to characterize these mass dimension and area size relationships that are more directly related to the true diversity of ice crystals in the atmosphere, such as looking at unsupervised learning methods. And so Joseph Koh, who's going to talk after me, is going to talk more about this work in more detail. So just to summarize, ice microphysical processes remain a major source of uncertainty in CAM6, and there's still both unknown physics as well as model representation that needs to be addressed. So as part of our work at LEAP, we're reevaluating past observations of ice processes to reduce structural uncertainty in ice microphysical processes using hybrid physics machine learning approaches. And we're also developing updated mass size and area dimension relationships using computer vision methods applied to this database of CPI images. So the next steps is to, integrate this new knowledge now into this an updated unified ice microphysics scheme, and then evaluate this against the previous CAM6 PPE. So I just want to say that we're definitely interested in any collaborations or ideas on this work. And so if you have any questions or ideas, then please reach out to me. And I just want to thank you for your attention.
All right, any questions for Kara?
You mentioned in your introduction about inconsistently treating the assumptions of the ice distributions and size in the radiative transfer and the microphysics exchanges. Is it in your plans to ensure that the radiative transfer is using what you're calculating here to be consistent?
Yeah. We haven't directly thought about that, but I mean, it's something we're definitely considering. But I guess like our first approach would just be to focus on the microphysics, but then also, but yeah, it would definitely be of interest to also think about, you know, making it self-consistent with the radiation scheme as well.
Hi, thanks, that's great. Could you say a little more about the advantage of the sort of hybrid physics, machine learning versus just pure machine learning?
Sure. I mean, so like, I guess with the pure machine learning, you have to, I mean, you could use those types of approaches for direct emulation, but here with the hybrid approach, we're still able to, you know, think about directly informing the functional form of, you know, what would go into a model rather than just like developing an emulator that we don't actually like know its functional form directly. Although there are, you know, now a lot of methods with things like symbolic regression to try to, you know, come up with a equation for what the neural network is predicting. But
I had a quick question about, if you go a few slides back, you had this time series predicted by node. Oh, they already, yeah, that one.
Yeah.
You have a lot of little ghost trajectories back there. Are those like previously trained neural networks? Or is this some kind of measure of uncertainty?
no, it was actually, I just plotted it as it was training the model. So those are just the different epochs as it was training, just to ensure, like for myself, that it was actually doing a good job of like sampling the parameter space as it was like finding the optimal parameters for this particular experiment. But so that's just the epochs during the training. It doesn't directly tell us about the uncertainty here.
Okay, thank you.
Oh, Andrew? So Kara, what would the default look like in that plot? Have you tried that?
We have, so yeah, I don't think I have the slides for that, but we did publish a paper in ACP recently where we were just looking at taking a bin microphysics model and then just varying alpha using either a constant value or this Nelson and Baker functional form for alpha. And it's in some of the experiments, it fits reasonably well to both of those models, but we found that both of those models in particular did poorly explain it, like for the colder temperature experiments in particular. But yeah, it would be useful to add as well what this alpha would look like with some different assumptions for the functional dependence.
All right, thank you, Kara. And it looks like Joseph is on the line. So can move on. Joseph is talking about related work on depositional ice growth models.
Hi, can you guys hear me?
Yeah, can you share your screen?
Yep, 1 second. You guys see that?
Yeah, if you're seeing, you can put it in presentation. There it goes, yeah. Oh.
Oh.
Yeah, it went back.
Good.
Yeah, you're good.
Oh, sorry about that. Yeah, so hi, I'm Joe. I work with Kara as well as these others listed here on the screen. I'm a postdoc at LEAP at Columbia, and today I'll be talking about how we could leverage machine learning to learn some more information about 3D attributes of crystals from cloud particle imagery. And we'll also briefly touch on how we can relate this to parameterizations, as Kara previously mentioned. So I'll spare you guys the details because Kara kind of already talked about that. But basically, cirrus clouds are challenging microphysically. They're poorly represented in models. They're microphysically complex. And a lot of this is due to the fact that ice crystals have various shapes that are hard to represent in like a bulk manner. We call this habit, and this is the function of its environmental conditions and how it moves through that environment. And it's been shown that habit can influence microphysical process rates, affect fall speeds, and also interaction with radiation. And in a recent paper from Jarvin et al. In 2018, they found that ice complexity alone could induce additional cooling effect of about -1 watts per meter squared. And to put that in context of the global CO2 forcing of about 2 watts per meter square, that uncertainty due to ice complexity is quite significant. So we have these CPI images, which are in situ measurements from various field campaigns. What you're seeing here on the left is these images that have been classified into 9 classes by previous work done by Vanessa Przybylo from University of Albany. And they used a supervised convolutional neural network to essentially, based on like hand labeled data, to categorize these CPI data. And based on that categorization here in the middle, you're seeing for these 14 campaigns, the fraction of these various habit with each campaign in different rows. And you see that there's a wide variety depending on what type of cloud is being sampled, et cetera. And so for this work, we were thinking like, how can we use machine learning to potentially learn more about its 3D features to improve the constraint of mass size relationships and connect that to the parameterizations. And in particular, we wanted to focus on rosettes because they make up a significant fraction of in situ cirrus clouds. So I'll just give you an overview of some work that we've begun to do. So in order to train some machine learning model, we need some data. And to do that, we essentially created synthetic data based on some a priori understanding of what a rosette looks like. Essentially some central sphere with some hexagonal columns sticking out. And then we can essentially create infinite variations of rosettes computationally by varying the angles of the arms and the aspect ratios of the arms. And then now we have some synthetic data that we can train our machine learning models with. And for preliminary data set, we have 9,000 crystals generated, but you can see, we can imagine we can generate infinite variations of crystals. And we end up with something like this. And I'll give you an overview of what this pipeline looks like. So for option 1, we can train a model to predict 3D attributes that we might be interested in. And for example, we might be interested in the effective density of this crystal, the surface area of this crystal, and maybe the number of arms. So we could, in this pipeline that I'm showing here, could extract some 2D features using feature engineering from the projections of these synthetic crystals, and then put that data into a tabular form with the features that you extracted as the input and the output that you're trying to predict those 3D attributes. And then in another option is to use deep learning for explicit reconstruction. And this has been an active field in computer vision for about the past decade. So basically what you're doing is you have these pairs of projections to explicit 3D models, and you train a encoder-decoder network to explicitly reconstruct a 3D model given a single or multiple views. So this is a more complicated option that we're playing around with, but for the sake of this talk, I'm going to focus on option 1 and briefly touch on option 2. And then once we have a trained model, the idea is we have unseen data, which is a single CPI image. We feed that through the trained model, and it will spit out some kind of prediction for a 3D attribute of interest. So to go into a little more detail for the pipeline option 1, we have these synthetic models. We can explicitly save these target outputs, number of arms, effective density, effective surface area. Then we take random projections of these synthetic models. In this case, I took 24 random projections. And then for each projection, we calculate some type of 2D feature that we think would be informative to predict the 3D feature. So for example, aspect ratio, area ratio, some measure of complexity, et cetera. And I have 7 for this example here. And that gives us 216,000 samples. We can think of that as a number of rows in the table. And now we have this in tabular form. You could use any kind of machine learning, traditional machine learning type of model to train that with 80% of that data, and then test that on 20% of the unseen data. So we could look at some of these preliminary results from this pipeline. we see for on the left, the prediction, the predicted versus truth for effective surface area, and on the right, the same for the effective density. And we see that a random forest that we trained can predict these attributes with moderate to high skill. And just to do a sanity check, just to see like what happens if we use a linear model, like is it actually better than a linear model? And we see that, yeah, it is modestly better, and it removes some of that overestimating bias if you just use a linear model. So this indicates that some nonlinear relationships are being captured by this machine learning model. And this is showing a confusion matrix for predicting the number of arms with the true on the Y and the predicted here. So in a perfect prediction, all of these and on the diagonal would be 1. So you can see that for some of these, they're confusing the number of arms for like adjacent, for example, like 5, 6, 7, and 9, 10, 11, 12. That's just due to the nature of this ill-posed problem. But it is encouraging that it's like kind of grouped in terms of its predictions here. And we see room for improvement here. So you see predicting the number of arms can be a little more challenging. Another thing we could do is instead of feature engineering and training a model, we can directly feed an image and use a convolutional neural network to predict those features as well. And just to show you some preliminary examples, we did the same thing using a 3-layer convolutional neural network to predict the effective surface area and effective density. And we saw that for the effective surface area, it performed better than the random forest, but it actually did worse for the effective density. So that's just to show like the empirical nature of machine learning is a lot of trial and error and experimentation. So, and this is a relatively simple neural network that we use, but you know, just to illustrate, like a neural network's not always better per se. And one thing I wanted to experiment with is what if we had an additional view, like how much would that improve? I mean, hypothetically, it should improve. But for example, we have these other instruments like the 2DS probe and the FIPS Halo, which takes stereo images of crystals. So thinking into the future, like, can we have some kind of automated pipeline to predict some 3D features from these observations? So we do the same pipeline, except we add an additional view for each synthetic crystal, essentially in each line of the table. We do that same pipeline that I described earlier, and we see that it does improve, and this is assuring that it does improve the performance of both effective surface area and effective density. And now, you know, even for effective surface area, we see that this R-squared is getting quite good. And here is for the prediction of the number of arms with 2 views, and on the right, it's hard to see, but all these numbers on the diagonal have improved. So that's reassuring. And just to briefly touch on this more complicated example option that I described, option 2, where we're doing explicit reconstructions. Essentially, we're using some architectures that have been developed in the past decades to see if we could transfer this to the ice crystals. And this is kind of work in progress, but just to show you here, this is like an actual 3D reconstruction from this single CPI image that I've used using this 3D R2N2 network that was developed like in 2016, which is kind of ancient in terms of computer vision world, but something that we just wanted to try out. And this is some ongoing work. So just to wrap things up, to use machine learning, we wanted to basically get a better understanding of the crystal's 3D attributes. And one way we can connect this to parameterizations is, for example, to connect this to single particle growth models. For example, some of these models being developed from Jerry Harrington's group at Penn State, and then constraining that also with the lab measurements, for example, those in the diffusion chamber. And then kind of related to what Kara was mentioning earlier, revisiting these mass size and projected area size relationships that have been previously discussed in these references shown here. And one idea is to replace, for example, the lookup tables with machine learning emulators in Pumas. And ultimately, we want to go down this route of implicitly constraining these parameterizations with these in situ observations and this machine learning pipeline. So with that, I will just conclude with these points here, and thanks to all my collaborators and funding sources here. And yep, that's it.
All right, any questions for Joe?
Joseph, thanks for this approach. I have a question to the second one. Why do you need the LSTM in the 3D convolutions?
So you're talking about here? Yeah, so the LSTM is to basically kind of capture the memory of the different views, if I'm understanding correctly. But this is just one type of architecture, but there's been various models. This is just one that we tested.
But the LSTM is usually for time, right? So it's a recurrent neural network, so you have kind of the time information. And
Right. I think it was just repurposed in this instance to capture the different views and not necessarily for the time information, the time varying information.
Okay.
Yeah.
Yeah, probably there are other ways, right? Okay, thanks.
Sorry, I didn't catch that.
It's just odd, but I'm just thinking of there would be probably other ways of doing this instead of using an LSTM, right? So,
Oh, right. Yeah. There's definitely a lot. I mean, there have been like lots of models developed. This is just one that I just happened to test.
Thanks.
I had a brief question. I don't know if there's an easy way to answer this, but I was a little surprised that density seemed to be easier to predict for all of these models than surface area, which surprised me a little bit just because you're feeding it 2D images. Do you have any idea why that might be? Or
No, actually, I do not know. I didn't really investigate that, but it's hard to know exactly what's going on with the machine learning model.
fair enough. I had similar surprises myself. All right. If there's no more questions, thanks, Joe. And next is David, talking about earthworks. So, pull up this. We didn't have the keynote.
No.
Yeah. Do we have to share your screen first? Yeah. Okay.
Oh, okay. Did you have to readjust that? That's good. All right.
And then go to the entire screen.
Oh, right. Okay, cool.
Just use PowerPoint.
Okay, I'll do that. Okay, thank you. Not only did the slides come up, but it's the first slide, so that's somewhat unusual. I'm here to give you an update on the Earthworks project, and a number of the first slides will be things that most of you have seen before, so I'll go through them fairly quickly. Earthworks is a 5-year project. We're currently in the middle of year 4. So it ends in summer of 2025. And it's a collaboration between CSU and 3 NCAR laboratories, CGD, MQ, and CESM. The split, as it says on the last line here, the split between CSU and NCAR funding-wise is 60-40, so not 50-50, but it's in the ballpark. The goal of the project, excuse me, is to develop a global convection permitting coupled model based on the CESM in a way that I'll describe. But this is not currently an official project of CESM. We hope that it will become that at some point. Earthworks funding is coming from NSF SISE, that's Computer and Information Sciences and Engineering part of NSF. But some funding from SISE is actually coming around from GEO. So the vision is to use a single 3.75 kilometer geodesic grid for atmosphere, ocean, and land surface at the highest resolution. So that's our target. And as you all know, this allows explicit treatment of deep convection and especially mesoscale convective systems, and explicit treatment of gravity waves of various types, including the ones that are produced by convection. We will include a resolved stratosphere, and we have the option of regional refinement in the atmosphere, ocean, and land surface on the MPAS grid. So they can all be refined in the same way. We will use the model to study both weather and climate. That's a hobby horse of mine now, on timescales ranging from days to years. And so it's possible to use a model of this type to understand deficiencies of lower resolution versions of the same model, or closely related models, or even very different models. Basically parameterize less and understand what the parameterizations are not doing right. It's possible to use the model to create training data sets for machine learning for use with lower resolution models. To develop parameterizations that work well with a wide range of grid spacing, let's say 3.75 to 120 kilometers, without changing the equations, without changing the code. So this is not something we can do today, but it's a really interesting scientific challenge that, in a sense, has been made possible by the advancing speed of machines. And finally, of course, it's still possible to run the model at lower resolution and to use it to study things like century-scale climate change. So the ingredients, the components of the model are the MPAS atmosphere non-hydrostatic dynamical core, which has been developed by M-Cubed here at NCAR. And we intend to use probably, mostly, if not entirely, CAM physics. Some modifications, but some of those modifications will appear in the CAM anyway, as time goes by here. We will be experimenting with WRF physics at some point, or some pieces of WRF physics, but we haven't started doing that yet. The MPAS Ocean model and CES model were both developed at Los Alamos National Laboratory, so this is Department of Energy Research. But that work was done somewhat in collaboration with NCAR M-Cubed at the time that the atmosphere model was being developed. So the dynamical cores for the ocean and atmosphere are very similar in a lot of ways. We are using the community land model on the MPAS grid, and we're using CMAPS, which is the mediator or coupler that connects the various pieces together, as shown over here on the right side of the slide. And we intend to use the community physics framework when ready, and that's being worked on pretty actively these days, so I'm hoping it'll be available soon. So our science goals are to resolve mesoscale storms, ocean eddies, and the other things listed here, and to study their interactions with larger scale circulations. Both the control of mesoscale systems by the large scale and the feedback of mesoscale systems to the large scale. We'll be eliminating the deep convection and gravity wave drag parameterizations, and as I said, resolving the stratosphere. And computational goals, the bottom line is for 2025, with a 3.75 kilometer grid, half a simulated year per day in atmosphere-only simulations with resolved stratosphere, and one simulated year per day in couple simulations with fewer stratospheric layers. And these goals have not changed since the proposal was written back in 2019. We will only be able to do this on a DOE leadership machine. This is not going to happen on Derecho. So the first 18 months or so of the project, we were building things. For example, a major job was to take the ocean and sea ice models from Los Alamos and put them into the CESM software infrastructure. So a new OPSI cap had to be created for the ocean model. for example. And that took a while. And then we were doing tests of things at low resolution and 120 kilometer grid spacing. So nothing like our goal, just to see that things work. So starting around the beginning of 2022, roughly 2 years ago, we entered a second phase of the project, and that's what this slide is about. Basically, as we increase the resolution from 120 to 60 to 30 to 15 and further, we encounter a whole range of problems. And many of these problems just come from the fact that CESM was not designed to be used at this resolution. So the software was written in a way that it doesn't scale. But there also have been some actual bugs. So these are some examples. There are more. But at one point, we had initialization on the 3.75 kilometer grid, actually, in experiments at TAC, the Texas Advanced Computing Center in Austin. It took 45 minutes to take the first time step. So from starting the model up to the first time step, 45 minutes. And if you watch the I/O during that period, it was not filling the whole 45 minutes. There was a long pause before I/O actually started. So very bizarre behavior and completely unacceptable. This was traced to an ESMF issue, and that's been fixed. So we found a problem and fixed it. And now the performance is much more in line with expectations. We had a 100 times slowdown in history I/O bandwidth. So you have history files and restart files. The history files are bigger, and this was traced, I believe, by Jim Edwards of NCAR here to a problem with PIO and fixed. And so we have reasonable I/O performance restored now. We were able to write restart records after some time, but then we couldn't actually restart them successfully. So that's no good. And this was also traced to an issue with PIO, and that's been corrected, and we can restart now. I'm going to show you a table later with some of these things on it. And then we ran into a problem which Brian Medeiros, who's here somewhere, was involved with, tracking down a problem with RRTMGP, that's the parallel version of the radiation code. And it turned out that there was actually a bug. There was an incorrect argument being passed in the GPU version, but not the CPU version. So that was identified and fixed and fed back to AER, the developers, and the results match now. And there have been more things like this. So you experience a problem, something isn't working. You spend some time to figure out why it isn't working, and then you spend more time fixing it. So it's like a three-step process. And some of these things took several months to get past each. So we have a software roadmap shown here, and it starts with March of 2023 up here at the top. Version 1.0 was released on GitHub, and I actually announced that in a seminar here in this room. Version 2 was released last November, just a few months ago. And it supported more things shown here. The red pluses indicate what's new. So 15 kilometer resolution, 58 levels, and so on. Support for the NVIDIA compiler and GPU version of the Pumas microphysics. 2.1 is being released today. Right? So I may not see it. Hold your applause. But bug fixes have been made, and we now have a 30 kilometer resolution certified that it runs on GPUs. And we also have a GPU offload version of the MPass dynamical core, the atmosphere. And I'll say a little bit more about this in the slides coming up. We're tentatively planning a version 3 for November of this year. There might be a 2.5 in June. You'll see that on a later slide. And then a 4.0 out near the end of the project. So what's in 2.1? That's the version we're releasing today. It includes the following improvements relative to 2.0, which came out last November. We have a GPU offload version of the MPES Atmosphere. We have been synchronizing the Earthworks code with the evolving CESM code. And CAM in particular, we're up to level tag 145, and at 2.0, we're at 124. So a fairly big jump there. We're using a patch to the aerosol optics for the NVIDIA compiler that will be replaced by something once the issue with the compiler is identified. And we have resolved an issue with MPES CICE with one of the compilers. We don't have the things listed in the second block here. We still have a problem restarting with the NVIDIA compiler. It's being worked on. NVIDIA wants a very small code that does the same thing that they can work on. You know? Not easy to do that, but we're working on it. And we do not have GPU offload versions of Club or RTMGP yet, but those are both in the works, as listed here. So in the next few months, we'll have those. So here's how you get it. You can take a photo if you want it. I'm going to click on the next slide here. The point of contact for issues is Don Daslick, who works at CSU. This summarizes a little bit more, gives a little bit more detail. Along the top here are listed 3 different compilers, NVIDIA, GNU, and Intel. And then under each of those, you have 4 different grid spacings, 120 down to 15 kilometers. And then there are various, CESM configurations, test configurations shown over here on the left side. And so green means it runs, and more than that, I mean, no known issues. Yellow means you can run it, but it won't restart. So if you may be able to write a restart, but if you try to read it and start up, it won't work. And gray means no supported precedent. So there's a lot of green here, but there's still some areas being worked on. This is for CPUs. This is more information about the GPU status. So OpenACC is the NVIDIA standard, basically directives inserted in the code, and OpenMP is offload is an alternative that will work with AMD GPUs. So our goal is to be able to use either one. We want portability, and we're working towards OpenMP offload for everything, but we're at the early stages of that. We started with OpenACC. So let's see, version 2 is shown in blue here, version 2.1 is in red, 2.5, which is listed as June of this year, is in the darker gray color, and then light gray means further out, like end of this year. Quite a bit is working now, but not everything. But we're able now to actually make use of GPUs and do scaling tests on machines that have them, like the ratio, and we're also working with Perlmutter, which is a machine at NERSC out in California, a DOE machine. I have a couple of slides here about Puma's, that's the MG3 microphysics on GPUs. And these results are courtesy of Jian Sun here at NCAR. So the first slide here shows that with a sufficiently large number of columns per node for CPU or per GPU, you get a certain performance measured here in columns per second. So bigger numbers better. And what you see is that on CPUs, the performance degrades slightly. Well, not so slightly, this is a logarithmic scale here. Whereas with GPUs, at low column counts, it's definitely slower than CPUs, but with sufficiently high column counts beyond about 5,000 or so, the GPUs are faster. And a little further analysis shows where the sweet spot is for use of GPUs. The blue line here, the blue line shows the boundary where there aren't enough columns per GPU to keep the device busy. And the red arrow over here shows that too many columns and not enough memory on the GPU to actually do the job. And green, which is in between, shows where you want to be. So Goldilocks or sweet spot or something like that. And that's called the balance point here. So just right balance, that's Rich Loft typing that. Balance point is about 30 kilometers with 16 GPUs, 15 kilometers with 64 GPUs, and so on. You can read the rest of it. So with 3.75 kilometer grid, we will need 1,000 GPUs, basically, in the current configuration. And that may be too many. Maybe it should be a smaller number, and that's being looked at. This slide is from Andrew Gettleman, and it shows the current status of a machine learning version of the warm rain part of the microphysics. And it's this panel up here is supposed to be an animation, but I'm using a PDF here, so that won't work. But what this shows is the growth of the peak in the mass distribution from a micron or so out to a few millimeters as the clock runs over a few minutes. This slide shows the a comparison of the emulated parameterization with a brute force bin model. And the agreement would be perfect along this diagonal line. And you can see that it looks pretty good. And then this panel over here shows large-scale precipitation frequency over the ocean. Control is in blue, bin is in red, machine learned bin is in green, and you can see they agree quite well. And then CloudSat, the observations, are shown in purple down here at the bottom. So at least in the tropics, the agreement is considerably better with either bin microphysics or the machine learned version of it, which is much faster. And the control is much worse agreement with observations. So this is coming in a few months. I just asked Andrew a few minutes ago when this might be ready to roll, and it's getting close. And actually, I think there's a newer version beyond what I'm showing you here on this slide. So, last slide, except for a few extras. We are thinking about phase 2. As I told you, it was a 5-year project ending in 2025. CSU and NCAR are talking about a possible follow-on proposal. Start date of that would be 2025. I can't say any more about it at this point. There's nothing really written except for just a few ideas sketched. But this is our current, one of the things that we're currently doing. So I will stop there. Thank you.
Any questions? Okay, I had a quick question, which is, what is the atmospheric time step that you're using with these different resolutions?
For 3.75?
Yeah, like how low is it?
I don't remember off the top of my head, but it's on the order of 10 seconds.
Okay, yeah, that's pretty small.
Dave, you didn't talk about the 7.5 and a 3.7 kilometer resolutions too much. Can you give us a picture what's happening on it?
Well, 7.5, there's nothing much to say. We've been working our way down from the top, but we've also done some tests for quite some time now at 3.75.
Yeah.
The 7.5 is an orphan at the moment. So on 3.75, we're able to run the model on Frontera in Texas, but we can't really get it to work here at Derecho. Brian Dobbins has been working on it with the idea of doing a diamond run. That's a goal, and hasn't succeeded yet. So there's software engineering issues. I showed you the one slide with the list of things. That slide's going to get bigger. Okay. So there's still some problems left.
Might actually be machine issues.
Sorry?
I think there might be machine issues, partly. You said software, I think it's partly the machine too, stressing the system.
Yeah, it's a new machine, but it also has new software.
But, I mean, there've been similar issues with TAC.
Yeah.
Along the way.
That's
So
right. We've had
I think it's
issues with
actually,
TAC too.
there are, he showed a bunch of infrastructure issues, I think there's more.
And currently, I was told this morning actually, that currently the model runs in CPU mode on Pro Motor, but not with GPUs, so that's yet another machine. Yeah, John?
Is the convection scheme ramping itself down, or are you just turning it off when you go from 7.5 to 3.5, the deep convection?
What's the question?
Is there some kind of scale awareness of the deep convection scheme, or are you just
The
turning it off?
convection scheme goes to sleep. I have slides that show that. They're quite old. I didn't include them here. But as you refine the resolution, the total precipitation globally doesn't change, but the convective part of it decreases by 90% or more, down to 3.75. So it basically goes to sleep, and our intention is to just turn it off.
But there is work also with MQ.
There is some work going on
making it
with
scale aware.
scale aware, and I have some ideas of my own about that too.
It sounds like it is scale aware.
What?
It
Well,
sounds like
it's
it
scale
is-
aware because there's a time step dependence,
Yeah.
because there's the fixed relaxation time, so that's what it causes it to go to sleep. It's actually not a resolution issue, it's a time step issue. So we wanna make it a resolution issue, so if you run variable resolution, you can get it to go in the other regions. So this is a joint discussion that we're having with Bill Skamrock, Dave, we should bring you in the loop, and Sean and some others of us in DOE. So everybody's kind of working the same part of this problem.
Everyone has the same problem of what do you do, especially in variable resolution grids where
Yeah.
deep convection wants
But
to
even-
turn off at like 10 or even 100-second times.
Even at a bunch of the diamond models at 3.75 kilometers, which you've probably seen when they shut off the deep convection, it doesn't quite look right. Then you kind of need something to help things organize because you're not resolving convection, you're permitting it.
Yeah.
So there's a real science question even at the 3.75 about what should be done.
You still need it, but it's not clear that current parameterization is what you need.
Yeah.
Exactly.
You need something. And I think there's more to it than just the time scale issue.
Yeah.
Other questions?
I have just one quick question, because you had mentioned that you've had some issues with like the NVHPC compiler. And so, and you had also mentioned that some of the earthworks software engineers were actually trying to work on a fix for them, which kind of, I was kind of interested in the interactions with the compiler developers, with the software engineers of the project. Do you find a problem and do you just say, fix this? Or what?
Well, in principle, yes, but you don't give them the earthworks code or CESM and say there's trouble with it. You give them something much smaller that exhibits the same issue. So they can see that their compiler has a problem in this little code, and they figure out what's wrong with the compiler and fix it, and then you're done. That's what they want, and that means we have to do work before they work.
Right, you gotta dress it up and show that this breaks your compiler, it's not just some CSM issue.
And you know, the motive for looking at all three of these compilers is we want portability. Not only that, but I mean, in trying to make it work on all three compilers, you can identify problems you might not find otherwise. So,
Thanks.
I'm wondering if you are thinking about changing the vertical resolution too, because if you use like the 32 layers with the
Yes,
3.75 kilometers,
I
the
know,
aspect ratio.
in CESM3 with CAMP 7, the goal is to support a 93 level model, and we intend to go there. But currently, we're doing a lot of our tests with 58. Okay, so our goal is to get there, but at present, as you can see, we're basically trying to kill things in the swamp.
But it is running with higher vertical resolution. It's just
Okay.
low top now.
Okay.
So eventually it's gonna get extended and once the infrastructure issues get solved. But yeah, it is a higher vertical resolution than the standard CAM.
But 93 levels actually don't get you better spacing. It's just adding a higher amount of top with additional levels, yeah.
Yeah.
I think it's actually identical spacing in the troposphere.
It's higher than 32.
Yeah,
higher than
it's-
32, yeah, right, but it's
The
between
I think
50
the 58 and the 93 are the same levels.
The same
of
levels,
atmosphere. Yeah, but it's higher.
Differences, it's more. Anything else? Okay, thank you all.
Just next we have, going to talk about changes to the spectral element.
So I guess this is kind of the closing DICOR discussion here. I'm talking about the spectral element DICOR, which is of course in CSM, as we know, and of course in E3SM. So the core of the development of the DICOR was actually together. Mark Taylor drove it, and then it came over to NCAR. For those who remember that history between E3SM and CSM. So I would like to talk about some extensions of that DICOR that are up and coming, and also how it's impacting the CSM framework. And this is joint work with my student Owen, joint work with the NCAR scientists you see here listed, and also Texas A&M, and also joint work with Mark Taylor, Oksana Guba at Sandia National Laboratories, and the Earthworks team, and David is here, and Jim Morel, of course, the Earthworks team, and you just heard actually how they tackled some of the high-resolution issues, and this was actually something we can leverage. So this is actually a really great contribution. All right, I thought I'd put in here Dynamics 101, yeah, for those who haven't really seen fluid dynamics equation for a while. Why would you even think about the change of the equations in the CSM DICORs? And I just want to kind of point you to this publication. This was a while ago by the UK Met Office. But when you think about what they call original equations, these are unapproximated Euler equations, and they are not necessarily on the sphere. So when we are actually looking at our models, we are on a sphere, and this is this G approximation. Yeah? So we are on a perfect sphere. And then we have actually choices to make, and I want to just guide you through these choices a little bit with a reminder what these equations are. Here are the names: non-hydrostatic deep atmosphere, quasi-hydrostatic deep atmosphere, this is the upper row, and then we have non-hydrostatic shallow atmosphere, and then we have the hydrostatic shallow atmosphere. We also call that primitive equations. Yeah? So for those who haven't really seen the equations, I thought I borrow this, I teach this to my students, so we can look at the equations again. This is now the approximation that's in here is just a perfect sphere, and we are looking here at a non-hydrostatic deep atmosphere configuration with, as you see, three momentum equations, continuity equation, thermal, this is the thermodynamic equation, and ideal gas law, and this is the best you can do. And this is where we want to be. Yeah. And we're not currently there. You see now what we are dropping typically. There is still an approximation here that G only varies in the vertical direction, but at least it doesn't vary. Yeah? So it's not varying in the latitudinal direction as it should, but we have the vertical, it's diminished basically in the vertical. And there are a few examples, code examples in the community. From ICON, which is a German weather service MPI model. MPAS actually has a deep atmosphere configuration, and MGAME will have this model. Okay, and let's go through some of the approximations to just really get an understanding what we're talking about when we say we want to expand the equation set. All right. So there is an approximation which is called quasi-hydrostatic deep atmosphere, and oops. Careful how I use this. So for that, you only really drop the acceleration of the vertical velocity and also the diffusion down here. This is pretty rare. I don't know any model that currently uses that, but that could be an option. It's not really popular right now. So what's really popular right now is this. I know you see a lot of those things that are crossed out. This is now called the non-hydrostatic shallow atmosphere equation set. This is actually design of almost all weather models that you find in the community. And what you kind of see here that we are now dropping certain terms, for example, let's kind of point here, these are metric terms, these are the spherical geometry of course, and really importantly also we drop actually cos-corious terms. So we drop these two and we only keep the sine-corious terms. And we also, whenever we see r is the distance from any point to the center of the sphere, we replace this with a, which is a radius, a fixed radius of the sphere. And that's now a very popular set, but also comes with this, basically we lose the variable g. So requirement now to actually keep the g constant, otherwise we are violating angular momentum conservation, energy conservation. So there's a consequence. And now I clean this up a little bit. So this is identical, I just want to clean it up a little bit. And then I make the last approximation, and that's the hydrostatic approximation on top of that shallow atmosphere approximation. And of course, this is super popular, so this is that, and that's really simple, yeah. So this is just getting rid of the acceleration of the vertical velocity. And this is how, this is how all climate models in a kind of CMIP umbrella are built. Yeah? So we can definitely have a climate model as a non-hydrostatic model. That's not typical. We call this now the primitive equations. This is basically how all CSM dynamical chords are built except MPAS. Yeah? MPAS is actually a non-hydrostatic shallow atmosphere, maybe in the future also deep atmosphere configuration. All right. So why would we even think about removing some of these approximations? And that's kind of my next slide. Yeah, why should we care about or expand this dynamical core equation set? Well, there are a couple of answers to that. I left some space here. So one is to enable new science, actually, that we could do with CSM. And what I mean by that, and the list could be longer, but we could, explore the predictability of the business system with a better equation set, so we have more confidence that we do the right thing. What I mean by that, we can, as Dave mentioned, we can. Oops, is there another pointer? We can, model across this climate weather interface continuously across all resolutions. That's also, that's also my next. This one. Oh, I didn't see that.
That's also the wrong button.
You want to point?
Yeah.
To the top button, but hold it down for a while. Okay, to wake up.
Oh, okay. Yeah, that's what the problem is, I think.
Maybe not.
Maybe not. Okay. I just shut up.
It appeared for a quarter of a second.
When I point the other way?
Yeah.
You can point at the screen too.
Okay.
Maybe it's just like
Let's see what
no, the top one.
Oh, top one. Oh, right.
Yeah.
Okay.
It was right.
Okay, I'll try this now. Modeling across this climate weather interface, which also means that we could then, go after these cloud permitting high resolutions. That's what Dave just mentioned, like a couple of kilometers. And also with this deep atmosphere idea, we could also go after a better whole atmosphere modeling strategy with folks at WACAM or WACAM-X with variable gravity and these additional cos-Coriolis terms. We also there's another motivation. We just reduce these approximations in the dicor, which actually makes us, or we hope that we can actually reduce constant biases or systematic biases. And there's, from idealized studies, there's an indication in the literature that actually this chronic double ITCZ problem that you might have encountered in CSM as well is related or could be related to the omission of the cos-Coriolis terms that we are doing currently in our primitive equations. So that could be, a fruitful avenue. And especially because cos-Coriolis terms are actually becoming super sizable. Super sizable, I mean 10 to 20% contribution. Yeah, so it's not just 1% or so at high resolutions, especially in the tropics where we have a lot of diabetic heating. And this is, again, coming from more idealized studies, but this could maybe point into the right direction also for our efforts. Also, we want to stay at the forefront of climate modeling here at NCAR at the international level. And our suggestion is to integrate a non-hydrostatic and maybe optional deep atmosphere configuration of the spectral element dicor into CAM or into the CSM framework. So this is kind of the idea. And let's kind of review very briefly what is the history of high-resolution modeling here at CSM. And this goes, let me see, oh, there it is. This goes, back 10 years back or so. But also I want to point out, most of this goes back to the old version of the model, which is CAM5 or CSM1. And mostly we had been looking in CSM, we had been looking at 25 kilometer resolution in the atmosphere, maybe 10 kilometers here in the ocean, and ice, often AMIP, some coupled, and here are some of the references. And the latest reference is actually here by Ping Shang, this is a Texas A&M group, and NCAR. They had this ITAS project, which also now contributes to this, CMIP, high resolution, high-res-MIP intercomparison. That is still ongoing, actually, here at NCAR. There were also attempts, even by our group here in Michigan, we went after variable resolution, and we were bridging down maybe to 7 kilometers or so. That was still hydrostatic, and that's really the big limitation. All of these simulations are limited by the hydrostatic scale, and Adam Harrington is also, of course, using maybe resolutions down to a couple of kilometers, maybe 5-ish or 7-ish or so, but it's a limit now, and that's what we want to remove with this configuration. Meanwhile, the international community moves quickly. We have, of course, high-res-MIP wasn't probably cloud resolving, but we have the Daniel project that Dave hit on, where we are now looking at 3 kilometers or 4 kilometers of resolution. We have NASA nature runs, there's Destination Earth in Europe, and this is now the new frontier and not the 25. And even in Japan and at ECMWF, we see the 1 kilometer now. So let me kind of show you. So this is from a diamond simulation. These are 40-day simulations. And here you just see a teaser image, of course, kind of cloud fields. And one is a satellite image. And yeah, you probably have seen this. It's very hard to tell apart what's a satellite-derived product and what's the model. And just to give you that impression, that is actually the truth, or I guess this is not really a prediction. It's initialized, yes, but we can't really now compare apples to apples, but it's just the features of the clouds that you should look at. And this, basically we have, realizations here of 3 kilometer measures, basically. This is even, and this is now coming from the IFS, the ECMWF group. Here we see a 9 kilometer, a 1.4 kilometer, and also cloud observations. And then, and the question came up, are we doing the right thing if we omit deep convection at the 9 kilometers? And that answer is probably out there. So, the IFS then was assessed with and without deep convection, and they conclude that deep convection is needed at those resolutions. Maybe at 9, easier to justify than maybe at 3. All right. Okay, let me just give you really an impression what we are doing and kind of really dive into the guts. Okay, this is what we are doing. We are taking an opportunity. This is actually now an animation from E3SM, or SCREAM, I should say. This is the high resolution option at DOE, based on the spectral element dynamical core. And this is just a loop here of the perceptible water and at 3 kilometers. So this is just kind of a demonstration project that this is indeed done. And this is done now with the non-hydrostatic version that has been developed by Mark Taylor and colleagues at Sandia Lab at DOE. And we are suggesting that we are now piggybacking on that effort. We are not reinventing the wheel. The suggestion is, and this is kind of the roadmap that just starts, well, it starts tomorrow actually, that we want to integrate the DOE non-hydrostatic dynamical core. Currently it's, well, they have a Fortran version and a C++ version. Put it into the CSM framework in CAM7 and really enable quickly cloud permitting resolutions with CSM3. And this could be a workhorse also for community release rather quickly, because we are not developing this DICOR, we are taking it from the DOE effort into the CSM world. Okay, and in addition, then let's really, and this is what Dave hit on, let's also put this model up to the test whether it can run on GPUs. And for this, we can then include in the second step the C++ and Cocos version of that spectral element non-hydrostatic DICOR, which is called SCREAM. And that really leverages their, the DOE functionality or capabilities, but also we can leverage what Dave just mentioned, the Earthworks GPU technology for physics. And we can bring that over, which is already, of course, in CSM. And also learn from them concerning physics tuning and options. Okay, and then we want to just use this. This is a 3-year project, but during that time, we want to use the Fortran version, also to, of course, present science results. For example, these mesoscale convective storm systems over here in the US, and coupled simulations over 40 days, these diamond runs for RC interactions. Okay, here's kind of how it probably is looking in the CEMA framework. So this, I guess I put a question mark here whether FE3 should be here in the future, but this is how it currently will look, or it does look. We have MPAS and SE as kind of the main cornerstones, and we envision that we will now give options. So it's just keeping the same infrastructure, but you have an option whether you want the old spectral element hydrostatic, the new one non-hydrostatic, or then the GPU-ready one in C++. So that's kind of basically, you use this now as a new variant. It's a new tool in your toolbox. Okay. There are many open questions, which I can't really address here, and I probably also only have a few more minutes here. It turns out, yes, I talk about the spectral element decor, but when you really look at it, when you look at Pierre's version that he published a few years back, and the non-hydrostatic version, which can be actually operate, or you can have a switch, or there's a switch in there. The non-hydrostatic version can be hydrostatic, so that's good news actually. So it's not necessarily adding computational cost from that angle, although non-hydrostatic is a little bit more expensive. But there are actually, the devil is in the detail. There are, differences in the prognostic variables. There are differences potentially in the vertical structure. Both can work with, vertically Lagrangian coordinates, but the non-hydrostatic can also be height-based one, not pressure-based. We have differences in the algorithms, for example, in the advection code now between the DOE version and the NCAR version. We have differences in moist versus dry pressure coordinate, and so on. So that does need attention. So to some degree, maybe for some of the improvements that Peter put in, we actually going a little bit backwards actually when we bring this in. So there will be these open questions. And then there are open questions, and we hit upon that in the discussion. For example, in physics, should we have deep convection on? Is Zhang-McFarlane actually appropriate? And so on for the high resolution. Some groups even want to switch off convection, shallow convection. That's pretty much debatable. I don't think that's our strategy. Gravity wave drag should probably go out the window, and we resolve it. Good news maybe for this team here, and there are many debatable things. For example, resolution, we hit on that. We probably need to look at that, when we scale the DX resolution horizontal, should we actually decrease vertical resolution? That's actually kind of an open question. The answer probably yes, but I don't think we might not be able to afford it. All right, okay. And I close with 2 more things, okay. This is just an image from DOE where it's very clear at like the 3 kilometers. These are now measurements of simulated years per day. This is kind of a performance measure versus computational nodes on Summit with DOE machine. And when you look at the green one, this is a 3 kilometer version, and overlaid is on CPUs. Overlaid is a C++ and a Fortran version. They are basically alike in their behavior. But you also see, even with the full Summit allocation, you don't really get a lot of performance. You are under, whatever, 0.1 years per day, where you really want to be, and that's really only possible with the GPUs, and this is demonstrated here in red. Once you switch over to this C++ Cocos version on the GPU, you basically, this is only the die core. This is not even full model. Full model would be more expensive, but here we get about 1 simulated year per day on the Summit machine with the Cocos GPU version. Okay, I want to close with another equation and then another comment, and then I'm really done. So the question is not just non-hydrostatic versus hydrostatic, but also shallow atmosphere versus deep atmosphere. And in order to make this a little bit more easier to understand, I thought I give you symbolically the equations as they're implemented here in the MSC dynamical core. And when you see these words, these are operators. So this is horizontal vorticity, horizontal gradient, and so on. And our strategy is to give basically, or to provide a deep atmosphere configuration without touching the operators. This is a choice. You can touch the operators, but we won't, because it's a well-oiled machine, actually, these operators. And the way to be and this is basically, you want to be really not intrusive. And the way to be not intrusive for the deep atmosphere is to actually just add these corrections in red. And you kind of see my definition here. R hat is just the R, the distance to the sphere, for any point to the center of the sphere, divided by A. And now you see that this actually now allows for this varying, well, as you go up into the atmosphere, a varying coefficient here. We also bring back the cos-Coriolis terms and some of the metric terms that you see here, but it's very little. And hot off the press, and this was last night actually by Owen, he did manage to show, and this is now a baroclinic wave test case from Ulrich, we have this prototype now running for the deep atmosphere configuration on the baroclinic wave. Here's now a depiction of some of the evolution of the surface pressure here over a few days, and this is 100%, well, I don't show you the shallow atmosphere, but that does look alike as it should at 1 degree with this kind of configuration. So it's with this, I wouldn't expect to see differences, but this is a good, it took us over half a year to actually get this. So this was a very big hurdle for us with boundary conditions. So again, devil in the detail. There's still actually a devil, which is we are doing explicit time stepping, which is really, really inefficient for non-hydrostatic deep atmosphere, and probably in the near future, in a few weeks, we have the IMAX version. I did. Okay, I just close this way. Yeah, we are working on an implicit with Oksana Buba from Sadia on an explicit. Explicit to implicit IMAX scheme. So we will speed this up big time. This is super slow right now. All right. Let me just close and I just go back one more time here into presentation mode. Yeah, summary. I didn't show you these science results, but what I showed you are that efforts are underway to expand the equation set in ChemSE, which is non-hydrostatic and deep atmosphere. Deep atmosphere is currently funded by DOE. That technology, of course, we can offer to the CSM project and make available here in the CSM. We will enable ChemSE to run on GPUs, and we will also, of course, benefit from all the model developments that have been conducted here by the CSU NCAR team, the Earthworks team. We will have science examples, and that's MCSs, nanoscale convective storm systems, and diamond-like coupled simulations for AC interactions. And that's actually, a topic for future CSM meeting, and I close here. Thank you.
All right, any questions for Christine?
So, point of clarification, could you go back to your history slide of the showing what's been done? Because you missed a whole thread. Oh, no, the next one. Yeah. So in addition to variable resolution CAM SE, for I think almost 5 years now, we've been running variable resolution CESM MPAS. So there's a number of papers by Xingying Huang on atmospheric rivers and tropical convective organization. There's one by Ming Chen on squall lines that's in development right now.
That's fair.
So there's a whole nother thread that's already doing some of that stuff at 3 kilometers in CESM with some of these same kind of science questions with MPAS. So that's another thread, and also in addition to what Dave showed too.
Dave, do you intend to stay with the moist hydrostatic pressure?
Good question. I think that's up for debate. So it will come in as a moist it's not decided, let's say this way. It will come back to us with the DO version. I think Peter will weigh in whether this would be viable in the CSM framework, and we anticipate potential changes, which DOE might want to entertain. So, yeah.
I see there's a question from Leo, it looks like.
Yes, do you hear me?
Yes.
Yeah, thanks, Christiana. I just wanted to offer a brief comment on the issue of shallow convection in the kilometer scale models. So the GFDLF V3 3-kilometer shield model has also experimented with deactivating the shallow convection. It makes significant changes in the circulation, some of them beneficial. For example, the intensity differences in convection between land and ocean. But it's obviously problematic in the sense, I think we know very well there are important things going on at those scales. So indeed a challenge for models operating at that scale. Thanks for your presentation. Excellent, really enjoyed it.
Thank you. Yeah.
So but how does that work? If you have a higher order closure scheme, right, like club, it's doing both the boundary layer and the shallow convection.
Yeah.
So if you have the boundary layer, you can shut off the shallow, but you can't really.
Yeah, it's not a viable option right now for us, I would say, but it's something that's discussed in the community.
Right.
This is just my lack of knowledge of things, but how are there clean tests of hydrostatic versus non-hydrostatic out there for some sort of more realistic things we're talking about here, so once you've got a full model? So you said, for example, that the CMIT models were mainly hydrostatic, but I mean, I know the Melvis model wasn't. It hasn't been hydrostatic for many years and hasn't had a hydrostatic option. And I don't know about the Diamond case, whether there were some hydrostatic models run at 3.7 kilometers.
No. IFS,
the European Centre.
Maybe IFS, yeah, the European Centre.
Yeah, the IFS one was.
Yeah, they had a hydrostatic option. They do have a non-hydrostatic switch, which I didn't activate. And they claim actually that they were pretty fine even at 5 kilometers.
I think it was that was the motivation of my question.
Yeah, I see various arguments in the literature. I even see papers now that claim that at 25 kilometers you should be non-hydrostatic. I think the word is out there.
So one note on your double ITCZ, I saw some recent NICM results from their 3-kilometer run like 2 years. So they ran it to do a climate run, and they don't have a double ITCZ in that model. Whether that's just the DICOR, or they have it in their low resolution. I don't know if that's.
Yeah.
And so you said this won't fix it at low resolution. It's only where the terms get large at high resolution.
That's the deep atmosphere. I'm not certain it's NICM deep atmosphere actually.
No. The cosine terms.
The cosine terms are related to deep atmosphere. We don't have a lot of examples for that. It is possible, and of course, LTCZ is complicated. It's a sea air, it's not just the atmosphere that plays into that, also the ocean under it. So it's not 100% clear that this is the only player, the Coscorio's terms, but it could be one of them.
Because you said there's a switch in this, has DOE done some experiments in this space? Have they kind of investigated?
Well, at the larger resolutions, they always run hydrostatic because it's cheaper and there's not a lot of difference. That's what they see. But at 3 kilometers, that's not hydrostatic. So I don't think this gray zone is, if you think about 25 kilometers or even 10-ish or so, that's not explored really well, actually. At which, again, we see papers that even say, maybe even it's more than 25, we should actually have. That came, I think, come out of PNNL, actually, those papers with Wolf.
I think Julio has been, no.
Thank you.
That's all. Thanks, Christine. And last but not least is Peter Luritzen, who's been our MC for most of this. And you'll have to pull up your own slides here.
Do you want to take a break, Peter, or you want to just go right into this?
This is the last talk and then we're done. So we can take a break if people want to. We can also just do this talk and pretty much be done.
Oh, you don't want to have any discussion?
Sure. I'll create some discussion.
Yeah.
So what is, do people want a break or not?
Go for it.
Where's my
There's 2 pieces of cake sitting out there. You want to run out and beat everyone to it.
application.
All right, so I would like to have a discussion with you, the community, about the future of dynamical cores in CESM. Just to preface my presentation, this is my view. This is not the official SEMA view or NCAR director view or all of that. It's my view. So I'm just going to start by setting the stage. You know, why do we or do we want to have multiple dynamical cores in CESM? As you know, we're a community model. We're not like an operational center, which leads to different decisions sometimes. I'd like to give an overview of our current capability. And then also I'd like just to highlight that, you know, a DICOR is not just this black box that we just import and then we're done. And I'm also going to illustrate that through some arguments I will put forward, just saying why I think CSM improves dynamical cores, and having several dynamic cores actually helps our workflow as well. So there's a lot of synergy happening. What I really want to talk about is getting rid of DICOR, maybe with an S, but at least the spectral transform dynamical core. And then I'll also give my thoughts of moving into the future. So, just a little reminder of some of the arguments of why you may want to have several dynamical cores in CESM. The argument that Rich always makes to me that I agree with is, if you want to assess uncertainty with respect to dynamical core, you've got to have more than one. Dynamical cores have always evolved together with compute platforms and architectures and so on, so there's always some dependency there. Our supercomputing environments are constantly changing, and DICORs can sometimes be very closely tied to that. It is my view that dynamical core science is not really settled. There's not like one numerical method that's like superior doing everything, although there are strong opinions in the community of what's the ideal approach. CSM is kind of unique in my opinion because we do enable dynamical core science to be done within our system. So you can run from idealized to pretty much full climate with many different dynamical cores, more or less. And also we're a community model. It's used for teaching. So University of Michigan has been running, it's called the Art of Climate Modeling that uses CESM and the DICOR functionality, and that's always important to educate the next generation. I'd like to point out this slide from Peter Nealon from the Weather Company from a couple of years ago from an AMS symposium where he pointed out, he asked a question, is a community supermodel with multiple dynamical cores possible? Unfortunately, the NCAR director did not bring up the CESM, but we have that functionality. I wasn't allowed to speak because it's a town hall. And also he pointed out what I thought was interesting, avoid model for my use only. So don't only develop your model for a narrow focus, I think he's meaning to say, but have it in a system where you can apply it in many different applications. So whether you agree or not, these are some of the arguments. So some years ago now, this is a slide presented to the SSC for a while ago. Like I thought it was a major achievement that now you could run these 5 dynamical cores, 3 of them scalable, state-of-the-art, 4 of them out of the box. And just create new cases, how you create a simulation CSM, you can change the resolution, and then more or less the model will run in various configurations, which is quite unique. We created this functionality because we kind of had the vision that we could go through a dynamical core comparison for CSM3, where we would run AMIP and couple simulations with all these different dynamical cores, and we set up an internal and external task team, not being DICOR developers, but people with expertise in evaluating the model, etc., to compare the different DICORs. However, we did not really get the buy-in from all the core developers, and we thought that was necessary do this exercise, so we didn't do it. So I kind of listed what a DICOR in CSM is ideally has to support. So for the very least, for our climate applications, we run 200 kilometer, 100 kilometer resolution, so like IPCC, standard traditional climate type setups. We run with lots of tracers, so the main cost of DICORs is tracers. We still need faster tracer transport scheme. Maybe we can sacrifice accuracy just to get faster transport, who knows? We also run higher top, and as I mentioned on Monday, I call it the death zone. When the lid is above 80 kilometers, you need some work to stabilize the model, and both MPAS and SC had to do work for that, or extra development to enable that. Then we have geospace, requires a DICOR for species-dependent thermodynamics. We put horizontal operators in, so you can do molecular diffusion, thermoconductivity in there, and through SEMA, MPAS is now also working on a deep atmosphere version of MPAS. So Christiana talked some about how to do that in terms of equations. Growing uses of the model is variable resolution. So, for example, there's the fully coupled dual polar configuration that Adam has been working on. All that is becoming quite popular. We also need functionality to only do vertical advection in the DICOR, so we can do single column experiments, which is also highly valued, especially from physics scheme developers. And then last but not least, we're, as the last two talks illustrated, we're moving into ultra high resolution where we need non-hydrostatic capability, which we currently have with MPAS in the system. I just thought it was funny to look back from my slides. In 2016, I was talking about moving away from CAM-FE. Here we are in 2024, and it's happening. I just wanted to illustrate it really takes a long time to support all this and work through all the issues that come up. So I just wanted to give a couple of examples of where there's interplay between all the applications of CESM, improvement coming from interacting with different groups, finding issues in the model, how all of that actually synergistically, I think, improves the DICOR and it improves CESM. So one example here is the early days when I was working on the SEC SLAM. We're running in Wacom. So this is the old Wacom, 70 layers. This is supposed to be the QBO. I'm not a QBO expert, but this doesn't look like a QBO. And if we compare that to the finite volume model, we're definitely degrading the simulation, and it didn't seem like we could just tweak some of these parameters to get a better simulation. And I kind of had the hint that, or the suspicion that the vertical remapping that we had was a little more diffusive than it should be. Didn't have the time to develop something myself, but we just imported the FFE DICOR, and they had actually worked pretty extensively in putting in a spline-based vertical remapping that's less diffusive. So I ported that over to spectral elements, and then now simulation looked better. Not as good as FFE, but it's getting there. I just wanted to illustrate, having these different DICORs in the same system can create this synergy where we move algorithms around. It's not that I couldn't go to the GFDL website, download the algorithm, blah, 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 but it kind of facilitates it. And higher vertical resolution, better QBO. So I also talked about on Monday, we're bringing in the MPAS DICOR. Now it's a constant volume model. The energy equation looks different, so CAM physics had to be modified, so our energy fix was using the right formula. There was a ton of stuff to be done in the couple, a lot of interesting science to be worked on, but and I went through it on Monday, some of it, but just wanted to say that improves CSM. Now it's much more general system, and it helps our workflow. Coupling to MOM6 has been very interesting because it now accepts explicit enthalpy fluxes, and then I've been working for a while to make spectral element using what's effectively a variable latent heat formulation which then needed some changes in the physics and now also in CMAPs in the coupler in order to make that coupling more consistent, at least between atmosphere and ocean. We haven't gotten to land and other components. But again, an example where there's an interplay of the whole system, making it better. Hopefully the simulations will be better too, or at least in terms of resolving processes. It also helps finding bugs, especially when you let the chemists run the model. Whenever I get an email from ACOM, I'm like, oh no. This is a slide from slide from Dr. Kinninson. I don't think I can explain all the details correctly, but you can correct me if I'm wrong. But I think N2O only has a source at the surface and a sink higher up in the atmosphere. So if you have that situation, you shouldn't have any gradients. But spectral element and in the variable resolution setup created gradients. So something is wrong. And after we were looking around for a while, Mark Taylor and I had put in these reference profiles to improve flow over orography. And I had forgotten to put it in for the advection scheme as well. And that was actually the issue. Also in terms of workflow, which is very important when you have supporting different applications and different dicores. So here's just one example. We've been working on a topography generation software. Julio and I and Adam and so on have been involved. And again here, we need to support CSM, which has multiple dynamical cores, so it's kind of built in. It will be dicore agnostic. A lot of modeling systems do not have dicore agnostic topography generation softwares. So it ends up with that you then use the same smoothing algorithm for all dicores. When you're running the model, they really see the same topography. And along with that comes all the subgrid scale fields for moving mountains and whatnot. And then again, interactions, I learned a lot from interacting with Skamrock and weather folks. And he said in passing, no, we don't smooth over ocean. Because then topography starts leading over ocean, and we're like, that might actually be a good idea not to do that. So we put that into our topography software. We hoped it would help our Labrador sea fees, because now Greenland wouldn't be 100 kilometers over the lap sea, but that didn't help, unfortunately. This software needs work when we go to mesoscales. So anyway, I just wanted to show you an idea of how everything plays together. And in my opinion, it really creates an environment where science moves forward. Okay, default dynamical cores and CAM versions as a function of time. It's pretty simple. We switched dynamical core between CAM3 and CAM4, and then it was finite volume, finite one, and finite volume. And then now here with CAM7, we are now changing to a more modern dynamical core. As I mentioned, it hasn't been easy. It's not like our long-term climate biases went away with changing dynamical core, so it's probably not the biggest reason why they haven't improved. But one thing I'd like you to note is that we have used the Eulerian dynamical core for single column in all these versions here. Meaning that even if I wanted to get rid of it, we couldn't, because we need vertical advection for single column, and it only worked for the spectral transform, the Eulerian dynamical core. John Truesdale, sitting over here, has been working really hard on getting this working for spectral elements, and fortunately E3SM has been doing this. We were able to steal some of it. Although our configuration here, we're making more extensive use of scene, so it's a somewhat cleaner implementation with respect to that. So now we don't need this dicore for that. I'm throwing it out to the community that I think that one is on the chopping board to get rid of, because we have a lot of dicores, it's not being developed. Although spectral transform is really nice for dynamics studies. So looking into the future, I like to look at it this way. What dicores are being developed? Active development. So we have CESM that I personally have put a lot of work into that will support the 1 degree applications for CESM3 and WACMX, and then we have the spectral elements without the CESM for various variable resolution efforts. We also have a NOAA project of adapting spectral element for Mars. That's also really good for the system because now you have to deal with a planet that has a different composition and so on. And making sure you don't have hardwired gravity anywhere, for example. NPAS, again, extensively used for SEAM applications, and then obviously for earthworks, being developed here at NCAR and being further developed actively. FE3, we had 3 years of funding bringing in the hydrostatic version in there. Took a lot of work with John and I to put it in. But it's had relatively little usage in CESM as far as I can tell. And we have no funded efforts for expanding the capabilities, so enabling the non-hydrostatic option in there or regional refinement. So it's not that FE3 is not being developed, it's just not being developed in terms of us being able to use it. And then Christiana talked about spectral element non-hydrostatic, so bringing in the non-hydrostatic version of spectral elements from DOE. I do not have any plans of developing CESM further after the CESM3 release. I don't see it feasible for me to bring in funding to put it on GPUs. I don't see it feasible for me to bring in a couple of project scientists to help me make it non-hydrostatic, et cetera, et cetera. So that's my current thought. It may change depending on what happens. MPAS, as I mentioned, actively being developed. Hopefully we'll have a geospace version not too soon. Remember, if we change to a geospace version, deep atmosphere, we gotta change chem physics again, because our vertical integrals are gonna look differently. So lots of work to do there. It's had GPU support for quite a while now. I don't want to speak on behalf of CESM and GPUs, but it's definitely something we should consider. Open questions about supporting that in a community model, because as far as I understand, it can sometimes be fragile codes. And then there's the non-hydrostatic SE that's actively being developed by by DOE, has GPU support, and it's using a different approach for putting the code on accelerators. So once we have that inside of CESM, we'll be able to compare different acceleration versions, and again, two fundamentally different numerical methods. So in terms of non-hydrostatic capabilities moving into the future, there are really only two dynamical cores as far as I can see it, and that's MPAS and SE non-hydrostatic. That was the last slide. Comments, questions, etc.?
So the original FP is already off the table, FP0?
And what off the table means. So first of all, as I mentioned on Monday, we support release codes for 5 years after release, so we'll be in there for that. We're building this new code base called CamSimmer, pulling over die cores one by one, so we pulled over SE. I hope MPAS will come in next. Whether or not we need FV over there, I don't know. I can tell you what my preference is, but it is a die core that's used a lot. It's really fast on small systems, et cetera, et cetera. So we have to make sure we don't step on the community's toes, so to speak. Rich?
I think you've said this before, but one of the jobs we have to do in terms of getting rid of particular cores is to say, if you use that capability with that core, this is the alternative with a different core, I think. Yeah, you've said this already. And I think if we lay that out, then it's kind of a softer landing for people to not use a particular core.
So Ila wanted me to send out a survey which I should probably do. And our CSM sibling models, web pages are showing quite a few spectral transform results, so we should change that to spectral elements to show that it's an alternative, so yes. What do you?
This may be more of a question for Cristiano, but I'm just wondering if all the infrastructure and stuff that's been developed over the last few years for regional refinement is gonna be immediately transferable to SE non-hydrostatic?
As far as I understand, yes. And I see it as a huge plus for CESM to get the SE core in there, mainly because of my lack of progress with supporting it. So the CSLAM version does not work for variable resolution. It's not because theoretically it won't have bandwidth to support it. And that also means you can run variable resolution with the physics grid. So if you want to run slightly lower resolution, you want to speed up the model. And then SE comes with what I think is as fast as it gets transport. It's based on the traditional similar Lagrangian formulation that basically what ESM-WF is using, and they don't want to move away from it because it's so fast. It's got fixes in there for various things that may be accuracy concern, but we'll have a look. So actually, I think for variable resolution, getting the SE non-hydrostatic in there would be a major plus. Also to make the model run faster, because variable resolution can be a beast if you have a lot of tracers, as ACOM would attest to. Andrew?
So Peter, you're now talking about SENH as if it's an entirely separate core. So it's basically bringing in another die core, even though because it's a different thread now from the SEC SLAM that you've done all the work on with the mass fixers and the energy and all that.
Yeah, we'll bring in the code as hopefully as an external. So it is bringing in a new die core, if you want to formulate it like that. But the whole interface with the die core, DOE is basically using older version of what we used to do. So there's a lot of stuff we can reuse there. And then all the work that Patrick Callahan and Adam have put into making it easy to set up variable resolution, application, all of that transfers. So we don't have, but that sense is not a totally new core.
Right, because it's the same grid, so all that infrastructure.
Yeah, and that's a biggie. Dave?
What about all the work you're doing for the enthalpy flux? You're gonna get it all work well with MOM6 and then.
So, that applies to MHAS too. If you want to do it the way we're doing it now, with variable latent heats and doing the coupling that we're implementing right now, then those die cores would need to adapt that. I've talked to Bill Skamrock about that in MPAS. He doesn't think that's particularly hard to do. And again, we've done it in our version of spectral elements, so if DOE would like to do it, we've shown them how to do it. But in the beginning here, before making all of these changes, we'll just run with MOM6 the way we're doing right now, with all the fixers. So, yeah, that's a good question. So, again, CSM can make die cores better. John?
This may be a not very intelligent question, but the physics, if I think about the grids of the die cores and things, there was a slide earlier on about you shouldn't develop a model to do one thing, and from an operational center you develop a model to do one thing. So I think it depends who you are, really. But where I came from, there was a lot of discussion about the development of the die core and the physics developers to make decisions on what the right grid to choose was, so that you were using the same grid. Particularly in the vertical, if you think about vertical grids, and there's really good reasons why you might want to do something, particularly about stratocumulus or something like that. But how does it work when you've got multiple die cores? Are you constrained to? Do these all use the same grids and so everything's fine, or is there an interface and you're not worried about it because it's not too big an approximation? I guess I don't really understand, that's why I'm asking.
I'm not sure I do either. So we've developed with mass coordinate, or pressure coordinates, if you will, forever in CSM. So with MPAS is our first experience with a Z-based vertical coordinate. We haven't really yet looked into what that does. And I think it'll be an interesting research because we're running the same physics with these different dicores and different vertical coordinates. I think there's a lot of interesting stuff to look into.
It wasn't just whether you use Z or Z, as you like to call it, and pressure or whatever. It was about whether you store the variables on the interface or in the midpoint.
Oh, the staggering.
Yeah, it's a staggering as well. Well, I think of that as a grid. Sorry, my poor terminology. So in the physics, there are good reasons to do them in. Where I came from, there was big arguments between the physics and the dynamics.
There's certain things you have to use both.
There are some things that you do need to
Right,
use
because when you start dealing with microphysics, and anytime you're moving anything in the vertical, then you kind of have to use both because you need to know fluxes and things like that. So
yeah,
the club has two staggered grids, so the physics is not all taking the same approach, given setting aside the dicores.
yeah, and then the microphysics takes in both and uses some of the interfaces for precipitation.
You're already interfacing grids, the staggering and the grids in some ways. I think there was always a perspective that the more you have to do that, the more inaccuracies you build. So you were choosing dicores to do it, but that wasn't quite.
Could be. I mean, it's pretty much agnostic, and most things are work in pressure, and can work on either grid or can get access to both. And so then once you're given a pressure coordinate, it doesn't matter whether it's hydrostatic or non-hydrostatic at the time, especially when the short time steps in the non-hydrostatic. You assume it's constant.
I wasn't even thinking about whether it was hydrostatic or not. They never had it. It was really about ways. There was really strong debates and arguments about ways stored variables on the physics and the dynamics.
Yeah. There's lots of research to do in physics dynamics.
Physics dynamics coupling group.
Yeah. Or there's a conference workship series that Christiana is part of.
Right, yeah, actually, if can maybe advertise. Yeah, we have a physics dynamics coupling workshop coming up in Exeter, actually, at the University of Exeter. UK Met Office is also a partner, of course.
You've been there.
That's in June, let's see, 18 to 20. Currently, submission for abstracts is open. If, we could probably, send out announcements again to this group to remind you. Yeah. There's one, maybe other aspects that I just want to maybe sneak in. When we bring in, I guess, a non-hydrostatic SE dicore, there is one component that's actually done in C++ already, which is the tracer advection scheme. So I don't think that's a big issue for us, even if we are doing a Fortran implementation. It will have a C++ code segment of the advection, but I think that's probably easier to deal with than a Coco C++ full configuration.
All right, I'll put my co-chair hat back on. So as you've seen, now this joint AMWG meeting with the other working groups has been very much about CSM3 development because we have a code freeze coming up. So this is probably not a good time to talk about future directions for the models and so on and so on. So that will be in a future meeting. So unless somebody wants to bring something up for discussion, I think we can conclude the AMWG meeting workshop. And remember to eat cake.
2 pieces of it.
It's gone. I think the cake's gone.
But thank you, everybody. Especially thank you for those online, those who have been traveling here. We really, really appreciate your contributions. And if you want to be more involved in what's going on here, or you want to give a presentation just like you gave here, please consider our Camp 7 meeting on Fridays, 10 a.m. local time. We really appreciate if you want to be involved, please be involved. Alrighty, thank you, everybody.